Good morning, everyone. Welcome back to the workshop in person or virtually. So this morning we got a session more on the data aspects and HPC storage aspects, which are very important for our community and for exploiting well supercomputers. We first have 3 talks, and then we'll have a coffee break at 10:15. And then another 3 talks, and then a discussion on the session, yeah. So our first talk is by Milan Klöwer from University of Oxford. Ah, you're here, yeah. So, yeah, go ahead.
Amazing. Good morning, everyone. Is it possible to... that's where my... Why is that one not on? Okay, that's perfect. Let's use that. Or should I just sit here? Oh, no. No.
Yeah. Better, sorry. No.
Sorry. Over here. Yeah, amazing. Good morning, everyone. I think my job is basically now to get a bit into this whole data compression issue that we're having while thinking about high-performance computing. And this talk is probably a bit more of like meta ideas about how we actually should do this. So kind of like the unofficial subtitle of this is "Nobody needed these bits anyway." And I know while this is a very flipping comment, I kind of put this out usually in order to kind of really question us which data should we store, and not just in terms of, let's say, variables, but also really on the bit level. So while we often talk about exabytes, now we try to look at the whole thing from the very different side, where we literally look at the zeros and ones. So you've seen this plot before. I think it came up on Monday already. Great, we had an exponential increase in computing power, yay. But we also had an exponential increase in data. And this is from ECMWF scalability program. So I think ECMWF stores now something like half an exabyte or so. And the questions are really obviously, A, how do we analyze it? How do we share it? And I mean, I think even ECMWF, they had to like get a couple of lorries together in order to drive their data from Reading down to Bologna, which is kind of almost ridiculous that you get the biggest bandwidth by driving lorries. But during these 40 years of progress at ECMWF, actually, next slide. Why does it not work? Yeah, here we go. Not much actually. So like during this time, and you see like picked up a plot there on the left. We went from these like black and white graphics to what we now call like digital twins, and where you really have a hard time to distinguish the model from satellite picture. But actually on the computing side, not really much changed. So we used 64 bits basically all the time, and only last year single precision 32-bit floats were introduced. And so really the question that I want to raise is, if we store this data, like what have we really asked us enough questions about in which bitwise representation do we actually store this data? So not just on the computing side, but then really talking about data compression. So as you could probably see already, this is a project that really spun off from this whole idea of reduced precision computing. And so we really try to ask the same questions for data compression. And I kind of like, as just in like an overview, I kind of feel that in data compression, there's basically 2 schools of thought. One is this like very physical perspective, where people always think in terms of trying to find the best basis functions to kind of fit our data so that we use it as little coefficients as possible in order to represent that. So like, I mean, spectral transforms, EOF, tensor trains are just examples of that. And they're obviously designed to somehow fit the spatial or even temporal structure of our data as best as possible. But most of the time, they're rather on the expensive side. Obviously, then, I don't know, you can use GPUs, but it doesn't mean that they're not expensive, just means that GPUs are really good at that. And most of the time, it's actually quite difficult to get the error bounds right. There's obviously done good work, but if the field that you actually want to represent doesn't really fit your basis functions, then you get often problems in terms of the error bounds. And if you think about, let's say, the spectral coefficients and you just want to get the data over, I don't know, Europe, you obviously have to transform the entire data from, let's say, the spectral space back to the grid point space, so you basically lose some of this random access. On the other hand, there's, let's say, the binary perspective in terms of data compression, where we really think about like the bitwise encoding. So you have a value, how do you represent it in bits? Then we talk about things like floats. Do you use some kind of linear quantization? What kind of entropy encoding do you use? We talk about things like lossless compression, and they're not necessarily designed to really fit the spatial structure, right? Because they're literally just zeros and ones, and you just think about a bit stream. But often the transforms are much cheaper. If you use something like floats, you get the really nice rigid error bounds from floats, and random access also is usually something that's a bit easier. So I just want to kind of like, as a rough overview, and I mean, I guess really successful data compression approaches would combine the two, but we're definitely focusing a bit more on the right one today. So one of the data sets that I've looked at in order to understand these issues a bit better with like real data is taken from the Copernicus atmospheric monitoring service. So you have variables like nitrogen dioxide, for example, where you can see there's a lot of different dynamics and features involved. So you even see ship tracks in the bottom at the surface, whereas you even have like signatures of like the sun, for example, up in the stratosphere and turbulence and so on and so forth. So yeah, there's like lots of different variables, and I basically just took them because I know there's like a lot of different things happening in them. So it's hopefully like a real case data set to kind of look at these issues. And how the compression is currently done for this CAMS data set, and this is basically the same for ECMWF's data as well, is that you use this approach called linear quantization. So you basically just take whatever floating number array you have, you look for the minimum, maximum, you split the interval in between, how many bits you ever want to use. For CAMS, it's 24. And then you basically use this like integer representation and store this data instead of the floating point numbers. And so if you look at this data in terms of the bit pattern histogram, so just asking the question, how often does every bit pattern in a given array actually occur? You get the plot on the bottom, where I've just like, you literally go from hexadecimal 0 to hexadecimal FFFFF, so just 000 to 111. And you see actually that in this data set, most of the values are really close to 0. So you can calculate things like the entropy of that. You see that the free entropy is something like almost 8 bits, so you're basically wasting 8 bit. You can immediately ask the question, what's the information in the first bit? And I can basically tell you it's going to be very, very close to 0, simply because you just looking at this histogram, you already know that the first bit, you basically already know that the first bit has to be a 0. Only in very rare cases will be a 1 where it's on the right. And so because the information is always bound by the entropy, you basically don't really have any information in that. Doesn't necessarily mean you can throw it away, because then you will get an error for the maximum value, but it already tells you that it's maybe not the best encoding. However, if we swap then to basically do the same thing, but instead of using linearly spaced intervals, use logarithmically spaced intervals, you suddenly get this picture, right? And so suddenly your first bit, because it kind of splits this histogram in half, actually contains at least a lot of entropy. What that means in information we'll see, but at least in terms of entropy. And you can see then basically the free entropy is much, much smaller. So kind of the idea that for this data set, actually, although CAMS basically forces it to be in this linear quantization, it doesn't really make any sense. You should actually encode it in like a logarithmic sense, for example, as we already do it in floating point numbers anyway. And so the question that we really wanted to ask is, if we look at these bitwise representations, what do we consider as like real information and false information? And basically, we came up with one way of how to define this, and we hope it's going to be really useful. And we already find it useful, but I hope then going forward into the future, this will be like a useful metric in order to really assess which bits we should keep and which ones we shouldn't. So here's just an example. Imagine you have some kind of field. If you represent this in normal decimal numbers, then let's say you have some values there. You see that the 0.05 is something that all of these values have in common. However, the trailing digits just seem to be somehow random. If I would tell you this is temperature, you would probably say like, yeah, well, we don't really care about the last digits because we know they're kind of like uncertain anyway. But the question here really that I want to ask is that assume you have a data set and you do not know its uncertainties. This is, I think, as far as I understand it, in many cases actually true, so that you basically just have a data set and you're just like, okay, I don't know what the uncertainties is, for example, because your model outputs like 1,200 variables and you can't really keep track of uncertainties in all of them. So the question is really, is there an objective way that we somehow find a metric that tells us, if we look, for example, at the bitwise representation of that, which of these bits are actually real and we should keep them, and which ones are kind of false, and you wouldn't even realize if they were all zero anyway. And so this actually maps directly to this issue of compressibility, because the bits on the left have some kind of pattern, so your lossless compression algorithm will have a much easier job in compressing that than the bits that are more on the right that I've kind of red shaded, because they're kind of a bit random anyway, so like there's no obvious pattern in it that the lossless compression algorithm can find, so the compressibility of the bits on the left is really high, whereas the compressibility of the bits on the right is really low, meaning that if you could throw them away, you would actually gain a lot because you've basically gained compressibility. So the way how we've defined this bitwise real information content is basically as follows. So assume you start with some kind of gridded data. By gridded data, I mean really basically the only property that is needed is that if you represent your data in the end in some kind of array, that the entries that are adjacent in the array also have to be adjacent in physical space. If you then basically, for every of these grid points, take the value, you look at it in terms of its bits, so like sign, exponent, mantissa bits, and for every single bit position, you analyze what the surrounding bits in the surrounding grid points are. And so you may, for example, end up in the following situation that, let's say the sign bit, let's say they're all positive values, so you have zeros everywhere for the sign bit, and so you basically do not have any mutual information in these bits. And so we define the bitwise real information content as the mutual information in bits between adjacent grid points. So really asking the question, if you know the bit in a given grid point, in a given bit position, how much does that tell you about the bits around it? And so, for example, for the exponent bits, you may end up in a situation where that if you know it's zero, that you know that the surrounding bits are also zero. Whereas then basically towards the trailing end of these bits, you end up in the situation where they're basically independent, and this is what we then basically classify as false information. So going down this, if you analyze this information content, and this is shown in this graph here, you have a maximum information of 1 bit. This is bound by the entropy you have in that. And so the real information, so what is the mutual information in bits between across grid points, is then what's shown here in blue and orange, and then the false information is exactly what's missing to get to your entropy. So real plus false would then be the entropy again. And so the question really is, and this is quite often the case, is that, let's say the last % of information is distributed across a couple of bits. Can you cut can you truncate your precision at some point so that you lose as little information as possible, but that you chop away as many bits as possible because you know that the entropy in these bits is really high, so they're really not compressible. And so what we often ended up with, and this is obviously a value that if people want to change it, they could change it, but what we suggest is that you aim for preserving something like 99% of this real information as it's defined here. And so the rest you basically would just round to 0. That gives your compressor a really easy job, and that immediately suggests you for a given data set its uncertainty. So you basically get immediately a value of like, oh yeah, this is the uncertainty that you should kind of like the error bound that you should preserve for your data set, and everything else is kind of too high of precision anyway. So we did this analysis, now here shown in colors, for all the variables in the CAMS data set. And this graph then actually, was quite a lot of information in this graph. So I've basically shaded in gray here now all the bits that do not contain any real information according to this metric. And the darker the color, the more information is in a given bit. So most of these variables, as you can see, are positive, so there's basically the sign bit is basically unused. There's a lot of exponent bits that are also unused, also in white. Then most of the information is then contained in the remaining exponent bits, and for some variables there's also information in the mantissa, and you see that some variables like CO2, for example, have actually a lot of information in the mantissa bit going up to like 12 bits or something. And this is because a variable like CO2 always is in a range within like a power of 2. So actually the mantissa is the bits in the mantissa are really the important information here, because otherwise basically all the values would be the same anyway. However, there's other variables, and you can see, for example, all these cloud liquid water content, cloud ice water content, all these cloud species that often, especially in the tropics, really basically change from one grid point to the next by really jumping by a power of 2 or so. So knowing more than a power 2 is kind of part of this uncertainty. And this is exactly immediately figured out by this metric. And so one of the bottom messages here is that while we use, let's say, the same precision for all the variables in our calculation, we shouldn't necessarily do that for our data storage. So there are some variables that just require higher precision, and there are other variables that require lower precision. Sounds somehow trivial, but actually I don't think that any one of us probably doing that. We probably throw the same precision. You do, great.
No, ECMWF is doing.
Well,
and
yeah.
We did in the old model, so the whole hydrological cycle was 24-bit, because otherwise you get bugs in the budgets.
Yeah.
And almost all the other variables were 16-bit.
Yeah, but I mean, that's like two levels, right? And so what I'm suggesting here that you really have for every single variable that you do something different.
And it's 40-year-old technology.
Yeah. Then one of the things that I found really interesting, so the plot on the left is the same as before, but this is really looking at the bits encoded in floating point numbers. So you start with the floating point numbers, and you literally just count all the bits and do this. However, this whole algorithm is completely independent of your bit encoding. So you can actually apply this to unsigned integers, you can apply this to whatever you want. And so I've basically repeated the same analysis by simply encoding all the values in the linear quantization or also in the logarithmic quantization. And so this immediately tells you that for the linear quantization, there's actually a lot of information that's just smeared out over a lot of bits, meaning that effectively you have to store more bits in order to preserve the same information, whereas for the logarithmic quantization, for most of these variables, it squeezes the information nicely very much to the left, so you basically could end up with fewer. So kind of basically saying, if you don't know what you're really doing, please use floating point numbers, or at least logarithmic quantization. If you know what you're doing, and there are definitely some variables that are absolutely fine to represent in this linear sense, and I think, for example, temperature is one of them, then you can obviously do that, but a default should definitely be something that's rather like logarithmically distributed, whether it's floats or you do something different like this logarithmic quantization, probably doesn't make necessarily a massive difference. And so spreading this information across bit positions is obviously really bad for your compression. And so we basically, looking at this here now, you can see how we've looked at a field, for example, this is water vapor, going from the left of 100% preserved information. So basically meaning you keep all the bits that your bitwise real information content tells you, going down to something like 80% of information, where on the right then we really end up in comic land. This is obviously not what we want to do, because then you get really these visual artifacts, but there's a sweet spot somewhere in the middle, and we usually suggest this is around 99% of information, where you get really high compression factors. These are now relative to 64-bit, and you still basically preserve your field, and I don't think everyone would have a really hard time to identify that this is the compressed field and not the uncompressed field. Then the question is always, because, sorry, going back again, the lossless compression that we've added here on top is Z standard. It's one of these developed by Facebook. You can literally use any lossless codec. I mean, you may get a different performance or different compression, but whatever's available. I mean, I don't really have hard feelings there. Use whatever you like. Because they act on the bit stream, you can basically walk in different dimensions first if you wanted to. And so we basically looked at these bitwise real information content in different dimensions. And you can see here that, for example, if you use longitude, you usually get quite high compression factors. Going into the vertical is usually not as much of a good idea because you have higher jumps and like your values change more in the vertical than they do in the horizontal. And there are even ways, for example, we combined that with the ZFP algorithm where you can basically compress several dimensions at the same time. And this is where you get really, really high compression factors. For example, if you compress space and time at the same time, then yeah, you get probably the highest compression factors that we found. However, you also have this problem that if you just want to have a 2D slice of your data, you have to decompress the whole thing. I see this as a big burden then probably on the data archive, but just basically put this information out. Compressing along longitudes is usually a really good idea. And if you can, then combine, let's say, the horizontal dimensions together. This is an example that this also works on slightly different types of data. So one of them is compressed, the other one is not. This is satellite data, brightness, temperature, that I think is from the Japanese Huawei satellite. And you can see basically that, yeah, there's not really, like visually, there's no difference that you could identify, but one of them is, I think, 15, 20 times smaller than the other. Basically playing the same idea. But what is actually happening, and this is basically a plot where it's just a zoom in on the previous one. So we look at Istanbul here, and this is just south of Istanbul. So it basically gives you the sea surface temperatures of Istanbul. And you can basically see that from the original data set from on the left to the right, what's actually happening is that the algorithm kind of finds out that there is some kind of like grid scale noise that simply is because of the measurement of the satellite apparently, and it kind of just filters that out and therefore gives you like a smoother field there. If you look at this in terms of the gradients, it basically filters out the insignificant gradients. So if that contains some information for you, then you may not want to throw this away, but I would assume that in most cases this like noise from the satellite measurement is probably not something we're necessarily interested in. So the typical workflow that we're suggesting is that for a given variable, you determine first the real bitwise information content. So for something like CO2, I know it's around like 10, 12 bits. You can obviously, for your data set, it depends a little bit on the resolution, but you can basically find that out. I've basically written down this reference implementation of this algorithm, the bitinformation.jl package, that I try to keep up to date with different things. And then once you know these bits that you want to keep, you remove the insignificance bit via rounding. So you can just use like IEEE rounding. There's different packages that can do that for you, and then you put some kind of lossless compression algorithm on top. So we've used that standard, but obviously, like a netcdf, that standard I think is only going to be supported in the next version. But there's like things like zlib at the moment already available. So you can basically just put that on top, and that will basically take care of effectively removing the zeros that you've produced in the rounding. And so there's a couple of advantages, I think, to kind of summarize that this information analysis you only do, let's say, once offline. It's fairly robust usually with, let's say, time if you run your time forward, but you could also calculate it online again if you wanted to. So this algorithm can like analyze about like 100 megabytes per second. So I think it's something that you can usually get into you can do if you want to doing your compression at the same time. So the rounding is usually very fast. You can use any loss like codec. If you use something like that standard, you get actually quite a range of size and performance. You can work with any bit encoding. So if you like this linear quantization, that's fine. But it's not necessarily a good idea, but it works. And you can still do any kind of like flexible chunking granularity. However, the disadvantages, and this is basically the stuff that I'm currently working on, and so I'm basically always inviting people to give feedback, is I want to understand whether this real information content is really well defined for any kind of data. So there are some data sets for which it absolutely makes sense, and I look at it and it's interpretable and I understand it, but I've definitely also seen some data sets that are where I really have to understand first what is the information that people actually are looking for in these data sets and what does this algorithm tell me. And this is, I think, really the stuff that I'm currently working on. And because most of our lossless compression algorithms are 1D, is also 1D. And so just to give you an example, I recently had this where I just want to compress some orography data at a given resolution. So I literally just like, I'm using Julia here, literally just using this bit information package. I just load the data, run the bit information algorithm. I get a plot like this. It tells me, oh, I should keep one mantissa bit. Sounds very low. Then I basically check, okay, what would happen to Mount Everest if I actually rounded to that value? Well, Mount Everest is then suddenly 600 meters smaller than it was before, but you can basically see this is absolutely within the uncertainty if you have a 10-kilometer resolution, and my office would be about 4 meters higher, which is the difference between this floor and the next, basically. And like NCO already has these things included, so you can basically just use these, and this is my reference implementation of this. So if you would like to use that and are interested in this concept, the issues there are basically the place to go to just show like, hey, this is what we've done. Does that make sense? And I would love to hear this feedback. And there's also a Python workflow example now coming. And this is a pipeline that Aaron Spring and Hauke Schulz at MPI have been developing, basically wrapping around my package. And these are just some other examples where this also worked nicely. We now support also mask arrays. You can also do this with like precipitation data. And thanks for your attention.
Hi, so we've got one question in the Google Doc. We've got Christian, who says visual comparison is one thing. I assume you also compare the statistical properties of the fields after applying rounding and lossless.
Yeah, absolutely. So we looked at different metrics. But the good thing really with floating point numbers is that the rounding mode in floating point numbers is quite bias free. So in the end, you don't actually do much harm to your data if you round it down. So things like mean variance are, unless you go like super hard and like, I don't know, only leave the sign bit, obviously, then you preserve that very nicely. We even looked at things like these, like other metrics, but actually I had the feeling that most of the time, looking at the data and you see basically if there's no visual artifacts, it's actually a really good proxy for you haven't done anything bad. So yes, there are different metrics, but actually looking at it is quite a powerful tool.
I've got one question in the room, yeah.
So my question regarding harm which you do to the data. I mean, after visual inspection, maybe it's okay. The fields look nice, but question regarding the ocean. Yeah. So you might see that the fields look nice, the currents are okay, but for some diagnostics, probably we rely on this false data, which other, because like for the ocean, I mean, we need to compute divergence, and then exactly where these insignificant digits might matter.
Yeah.
Right, because you have, I mean, it's and the same applies for the ocean heat transport.
Yeah.
Yeah, it might say that U looks okay, temperature looks okay, but you compute the heat transport and you see that it's not conserving. So like this divergence thing, so would be maybe one of the good metrics.
Yeah. Maybe one thing I should highlight here is one thing I really like about this approach is that you actually encode the uncertainty in the data itself. So meaning that instead of just say you have single precision numbers, you don't know where your uncertainty is because you've rounded it. Basically, people can afterwards look at it and see like, oh, these are all these values are 0. So you basically communicate the uncertainty within the data itself. So you kind of already have an error bound on your data that you communicate with the data. That obviously, in your case, you may need to like propagate that to see like, okay, where's my error bound? If you are actually interested in preserving the zeros and ones in your false information, then obviously this metric, you haven't applied this metric then in the right sense, because for your case, then it's not real and false as we've distinguished it here, right? So it would be, we would basically need to like differently define this metric than in your case.
In most of the cases, we differentiate. And another question would be, then it comes out, yeah? So, I mean, it's...
we got quite a lot of time for discussion. We got quite a long discussion session after, so I think we're going to move to the next talk to Javier. Thank you very much. Thanks. So our next talk is by Xavier Yepes from Barcelona Supercomputing Center.
Hello, I'm Xavier, and I'm going to present the activities related to lossy compression that we are performing here at BSc. As you know, the increase in the forecast capability of our system models is strongly linked to the spatial resolution to solve more complex problems. So, as a consequence, this requires a lot of computing power. So, this can generate a large volume of data, and this has implies three main points. Regarding the point of view of data. Data must be efficiently written into the storage system. We cannot afford more offline post-processing like we do since now, because the raw data will be very, very big. And this has, of course, a consequence, which is the cost, the very high cost of storage systems, like having spinning disks, a storage system of spinning disks. So in this new Exascale era, it is very important to have an efficient management of the I/O. As you can see in this plot from ECMWF, which illustrates the archived data. As you can see, over the years, the data has grown a lot. So this is a problem, and we have to deal with it. So, well, in that sense, there is the XIOS I/O server, which is the I/O issue is typically addressed using scalable parallel I/O solutions. In this case, XIOS, which is a known and widely tool used in the European air system modeling community. And XIOS, which stands for XML Input-Output Server, is an asynchronous MPI parallel I/O server developed by IPSL. And this nice tool has these features which are targeted for climate modeling. Output is in NetCDF format. The data is CMIP compliant. And also, this tool is able to post-process data in line to generate many different diagnostics. If we have a look on the technical features of XIOS, XIOS is meant to address the inefficient read-write process of the old sequential I/O schemes, and also the unmanageable size of the raw data. How? Well, it implements scalable parallel I/O, and also, as I said, offering inline post-processing. In addition, XIOS also offers lossless compression using the gzip utility, which comes with HDF5. In our case, we use as a test case OpenIFS and XIOS. OpenIFS is an atmospheric general circulation model developed by ECMWF. And some years ago, not many, but we integrated XIOS with OpenIFS to address the problem that the OpenIFS model had with the sequential I/O scheme. In this paper, we explain this development, and also we proved that the overhead of outputting data through XIOS is really small if we use current resolutions. But and as I said, in the future, the resolution will grow, so the data output will also grow. So this will probably become it will become a bottleneck, so we have to address it. So in that case, we also tested the default lossless compression of HDF5, but it doesn't fit our needs. On the first hand, the compression ratio is too high, so if we use a compression ratio high, it takes too much time. So the total execution times takes too much. And on the other hand, if we want to have a reasonable amount of time, the compression ratio is not good enough. So, well, this is the scheme of the integration. There are the IFS processes or OpenIFS processes which run an XIOS client instance, and those clients are communicate data to the XIOS servers using asynchronous MPI communications. So, are these MPI these XIOS server processes which are in charge of compressing data. So compression is done out of the critical path of OpenIFS. So here there are some numbers regarding the default XIOS compression. In this case, we are running a TCO 255 configuration, which is about 39 kilometers in the horizontal resolution. And in that case, we run two XIOS servers in one node. This means that we had two of these MPI processes for the XIOS servers. And on the y-axis, we have the total execution time of the simulation, which means the OpenIFS simulation plus the cost of outputting data. And we have different scenarios. The first column is with no compression to have a reference, and the second column is compressing just 3D fields: CLWC, CIWC, and CC, which are characterized of having a lot of zeros, which means that they are very compressible because it's very easy to compress zeros. So in that case, the compression in the red line, the compression it's good, and the execution time doesn't increase at all. This is because they are very compressible. However, if we try to increase the number of fields that we compress, instead of 16 fields, the compression ratio doesn't increase too much, from 39 gigabytes to 32, but the execution time, it increases a lot. In that case, although I said that the compression of data is done out of the critical path, because it is done in the XIOS servers, however, since the servers are busy compressing data, the clients of the IFS processes cannot send data because they have to wait until the servers finish the compression of the previous time step. So, yeah, at the end, it increases a lot the execution time. In order to address this, we increase the number of XIOS servers. So, instead of using 2 XIOS servers, we use 8 XIOS servers to have more computing power. So in that case, of course, the compression ratio, it's the same, but we can decrease the execution time. If we have a look in this plot, it's the same as the previous one, but we are using a TCO 511 configuration, which is about 23 kilometers. And, as it happens again, in this case, when we try to compare 3D, if we compress 3D fields, the compression ratio is quite good. However, when we try to increase the number of 3D fields to 3 to 19, the compression ratio doesn't increase too much. Note that this plot doesn't contain a column with, like this one, without, we are using 2 XIOS servers, and in that column we are using 8 XIOS servers. So the execution time is not increased too much because we are just increasing the servers. We can see clearly this in this plot, which is using a TCO 1279 configuration, which is about 9 kilometers. And as you can see here, in this case, we are if we compare with 5 3D fields, which have a lot of zeros, the compression ratio is quite good, and the execution time doesn't increase. But if we try to, for example, in this case, this is just putting a lot of pressure to the servers to see what happens. And as you can see, the increase in the execution time, it's very, very big. So we have to put a lot of resources. In this case, for example, the original configuration is running 20 XIOS nodes and 2 servers per node. So this is 40 XIOS servers. But in this case, instead of putting 2 XIOS servers per node, we are putting 16 servers per node. So we have to increase a lot the computing power to have a reasonable execution time. So, well, seeing these numbers, we considered using lossy compression. In this case, we wanted to test the EZ compressor developed by the Argonne National Laboratory from the US. So we started a collaboration with them to explore if this compressor is suitable for XIOS regarding these 3 points. Well, first, we wanted to achieve a high compression ratio. This is very important, but maintaining the execution time. So this means to have a very good compression speed to mitigate the I/O overhead, but also keeping high accuracy of the compressed data. So, as you can see in this plot, EZ is very nice because it is registered as a third-party filter of HDF5. So in XIOS server, in XIOS, which uses the NetCDF library, and NetCDF4, it's built upon HDF5. So in this kind of workflow, we can see that HDF5, instead of using the gzip default lossless compressor, it's using the EZ filter. So in this plot, we can see a comparison between gzip and the EZ compressor. This is just preliminary results, so much more research is needed. In this case, we can see that, if we only compress, this is using a TCO255 configuration, a small one. And, if we compress just these 3D fields, which are very compressible, the compression ratio between both algorithms, it's more or less the same. And the execution time doesn't increase for, neither of them. But if we try to compress 16 3D fields, the compression ratio of the gzip is not very good, as we saw before. But in particular for EZ, the ratio of compression is very high because we go from from the no compression scenario, which is 43 gigabytes, to 0.89. It's important to mention that we are using compression level 6 for gzip and a relative error bound of 0.01 for EZ. So, take in mind that this is a proof of concept, so we are not scientifically validating these results. I mean, we are just first validating from a technical point of view that it is possible to use these kind of tools in widely used tools like XIOS. So, if we want to, again, for the gzip, if we want to reduce the execution time, we have to increase the number of computational resources, in this case, using more XIOS servers. So in this case, we have to use, we are comparing 4 and 8 servers per node, respectively. So in this way, we can reduce the execution time of the version which is using gzip. As I said, for example, in these 2 images, we are using an error. We are setting an error bound of 0.01, and we are the EZ tool is maintaining this error bound within the limits, for example, for the specific humidity and temperature. But again, this is a proof of concept, and this is just a pure technical validation, not a scientific one. So in that sense, well, we can conclude that the results are promising because the Z lossy compressor is faster than the default gzip, and we can have a much higher ratio, compression ratios. In addition, originally the Z compressor could only apply one error bound for all the variables, but we have different needs depending on the variable, or in our case, the fields. So, well, they added support to set different compression parameters for each field. So we have to change XIOS code to individually read all the different compression parameters and set the SZ filter via NetCDF. So this will allow us to tune the accuracy of each field depending on scientific needs. So regarding, well, in the line of this point, we have to discuss with climate scientists, because this is from a technical point of view, which is the adequate compression parameters, which, well, known as error bounds, for each field depending on the acceptable errors. Also, we want to test the SZ filter with the new HDF5 parallel I/O to just output one NetCDF file instead of as many NetCDF files as XIOS errors we have. And well, and finally, this work is in a very preliminary stage, so we have to further explore and extend in the upcoming projects like the recently approved ERI project. And that's all. If you have any question.
Do we have a question in the room? I've got a few questions, and so for the gzip filter, you did not test it in parallel. You just tested it sequentially, yeah.
What do you mean sequentially?
Well, when you do the you did the compression per I/O server. You did not use the parallel I/O interface from NCDF.
No, because in XIOS it's not possible. If you are using the parallel I/O, it's not possible to enable compression. So since we are writing one NetCDF file per XIOS server, we are using parallel compression because each XIOS server is compressing its own subset of data.
Yeah. But as you mentioned at the end, there is a new parallel I/O interface in HDF.
Yeah, because
5,
this new parallel I/O in HDF5 it allows you to compress data even if you are writing just one NetCDF file. So we want to test this new feature in HDF5.
Okay, thank you. Sophie?
Yes, any interaction with IPSL, so to include possibly this new other type of compression in XIOS officially?
We haven't talked about this because this is very preliminary work, and we first wanted to see if it's feasible to use a tool like SZ in XIOS, and if it's the case, yeah, we would be very proud. I mean glad, happy to include it in XIOS. Yeah.
This is a long time I would like to look to this aspect, but I don't have the time to doing it. So I'm very happy you do the job. And of course, it will be great if we can integrate it into XIOS in the future version.
Okay.
Yeah.
Right. Thank you. Oh, one last question.
So you used like 16 XIOS servers, right? I could imagine if you're writing independent files, you could also use as many as the work, whatever demands. Like if there's 20 processors used for whatever model run, then you use 20 XIOS processors and it'll scale well, right?
Can you say it again, please?
Because if they are in a node, if your work uses 32 processors, you would also need 32 XIOS processors, then it would scale very well, right? Because you're writing independent files. Each of the XIOS servers is writing its own chunk.
But I mean, the model can use, for example, let's say 500 processors, but you can have just one XIOS server. I mean, it's...
I'm just wondering how it scales, generally. What's the limits of... How do you know to use 8 or 16, or what's the number, and does it have to be on the same node or different node? How do you know those numbers?
This is a try and error procedure. I mean, it's very difficult to know a priori how many nodes and how many servers per node you have to use to find an optimal setup. You have to test it. I mean, you have to try different options. Yeah, it's... you probably agree with me, Jan?
Yes, in fact, it depends on the amount of data you will output. And so,
exactly.
More data you have, more server you must...
yeah, there are a lot of different...
To overlap the computation by writing or by compression. So compression is take time, so you must use more servers. It's up to you to find the good compromise between output size and performance.
Yeah, there are many different parameters that you have to be aware of to find the optimal setup. So after doing this procedure many times, then you have a little bit of experience and you can imagine more or less the numbers, but at the end you have to try it and run different setups to know which is the optimal one.
Thanks. Okay, thank you. Thank you, Olivier. So now we got Tiago Quintino from ECMWF, who is joining us remotely. Hi, Tiago.
Hello. Hello. Hi. Good morning. Can you hear me?
Yeah, we can hear you.
Good. Yeah, I will. Okay. Oh, sorry. Apologies. Okay. Can you see my presentation?
It hasn't appeared yet.
But yeah, go ahead.
Go ahead. You can start. Yeah. It will.
Can you see it?
It will appear. Yeah.
Okay. Good morning. I'm very sorry I was not able to attend the workshop physically. I would love to have met you all and discuss all these interesting subjects. Thank you for the invitation. Also, I will be speaking about the approach of ECMWF is taking with respect to data-centric workflows as we approach exascale weather forecasting. In particular, I will also discuss how this connects a little bit with the program that is called Destination Earth that we are involved with. I mean, very quickly, you know that probably that ECMWF is an international organization that runs an operational weather forecasts service, and we run that four forecasts, ensemble forecasts every day, as well as operating 2 of the Copernicus services. But what you may not know as well is that ECMWF is one of the organizations that is responsible for the EU Destination Earth program. It started in January 2022, and our job will be to coordinate the building of 2 digital twins, the 2 initial digital twins. There will be more later on. One on weather extremes and one on climate. In particular, the weather extreme digital twin will have daily runs and will be a kilometer scale weather forecast, very likely we hope we will be able to run a 1 kilometer weather forecast daily. This is today a very extremely ambitious goal, but we need to be prepared for that. And today I'll be discussing a little bit the things, this research that we and the developments we have been putting in place to arrive there. So to help us understand that, I will very quickly show you what entails ECMWF, the production workflow, and what we do at scale. So we get observations every day from satellites and all over the world, roughly 200 million observations per day. We ingest that into our system model. When the IFS, which is our model, runs and finishes, we have roughly produced 120 terabytes per day of raw data, of which we then process for user-defined products around 45 terabytes per day. And then we disseminate that all over the world. In destination Earth, you can imagine such system running once a day, but on that place, the Earth system model will produce roughly 1 petabyte per day. So once a day, we will run one forecast, and that will be 1 petabyte. And we need to be able to handle this. But this is a big challenge, because if you look at if you zoom in how this works, today when the IFS model runs and we produce all this amount of data, it goes to the parallel file system. And I think this is kind of like what we expect of our HPCs to do, right? And then from there, our product generation reads those fields and that raw data and produces more products, which, surprise, surprise, end up in a HPC parallel file system. And then from there, we do dissemination and we send them all over the world. On the side, we also have to read all that and put it to the perpetual archive, our Mars system. What's crucial is that in that time window, there is a time critical path, if you want, where within minutes of producing that output of the model, we have to run post-processing. We have to use that data within minutes, and we are reading roughly 70% of it. So 70% of 30 terabytes 4 times a day, that's 120. We read 70% of it within minutes. So you can imagine what's the impact of having to read 70% of 1 petabyte within minutes, right? So this is the big challenge we face. And why is that a challenge? It's because if you look at this table, it's a test we ran a few years ago. We emptied all our HPC, and we ran on our current operational HPC a 50-member ensemble at 9 kilometers. So something we cannot do today, but we will soon be able to do when we migrate our system to our new data center in Bologna. But we ran the IFS model without I/O, right? And we get some time, say 5,700 seconds. And then we turn on the I/O of the model, and just simply turning on the I/O, the model runs 17% slower, okay? Which is, it's acceptable because you are doing some more. We do have an asynchronous I/O system with an I/O server, but still it does slow down the running of the model. What's interesting is if we turn on the post-processing at the same time. So post-processing is a completely independent process in the HPC point of view. So completely different job. It's just that it is linked to the whole workflow by reading the data as the model is writing the data. And just because of contention of the parallel file system, the model itself runs even slower. So this is really a workflow, contention on workflow, affecting all the components of that workflow. And that tells you that you really need to think of workflows. You really need to optimize everything, be a holistic optimization. Doesn't matter if you can produce the data faster if you can't use it fast enough, okay? So we need to have this data-centric view of, so in a way, you see, there is this coupling of the file system. And the reason is we really use the file system for everything on our model. We acquired the observations, we put them in the parallel file system. We run our system model, we produce data, we put it in the parallel file system. We do our product generation from the parallel system. We do simulation from there. Even data analytics. If you want to run machine learning, you'll have to do it on top of that. And then when we archive from there. So you can really start seeing the pattern here is that data is central. Data is only as good as what you do with it, okay? So I think we have been as a community, very focused on the compute part of generating of the data. That's because that's where the science is, and it's what a lot of work goes into that, of course. But we have also to think, how can we make data more useful? How can we make that downstream of producing the data, our data is used at scale? And when I talk at scale, I'm talking about 1 petabyte a day type of scale. How can we get there? So in the Destination Earth program, ECMWF has one particular task, which is to develop what we are calling the digital twin engine. So what is that? Because it's a bit of an abstract concept, and I've had quite a few questions about that. So it's really, it's kind of like a framework for Earth system model workflows, okay? So think of it like a game engine, right? You have this Unity or Unreal Engine for people who design games, you know, you don't have to rebuild from scratch a 3D engine if you want to do a game nowadays. So it's, in a way, is a bit like that. It's an engine for Earth system workflows. It's a framework. So it's not model specific. It's not only for the IFS. We hope that can be reused for other models. It's a collection of APIs and services that you can use and for doing various different things about workflows, but it's mostly designed as an opt-in component. So you don't have to buy and use everything at the same time. You can just use part of it, okay? So, so what components are those? So we have a workflow manager, you can use it if you want, data structures, parallelization libraries. We are going to design some infrastructure for model plugins to allow, for example, post-processing within the model, but by third parties. In particular, we've been investing a lot in our key value object store and with semantic data access. We call that the FTB. And today I will speak a little bit more about that. We have been working on an I/O server, which called multi-IO, a data notification system, and some accessing data via DataCube APIs. Speak about that today too, and APIs, for example, for post-processing. So all this will eventually come in fruition over the next coming years with the efforts and investments in Destination Earth. Some of these are already there and available and open sourced. And today I'll speak about these 3 that are bolded there. So the FTB is basically a domain-specific object store. It's really just for weather and climate. It's the offspring of an European project that finished in 2019, of which Barcelona Supercomputing Center was a partner. Was NextGen.io. We had access to this very novel architecture at the time, some HPC nodes with NVDIMMs, just fresh out of the factories. These nodes are still available. It's a research infrastructure. You can apply to run some research there. It's hosted in EPCC in Edinburgh. And we use these nodes to demonstrate that our object store could use these novel storage class memories to scale well and our forecasting system. So we developed this FTB. It's basically a domain-specific distributed object store, transactional, no synchronization. It's a key value store where the keys are the scientific data. So you use keys like get me temperature rather than providing some weird object ID that humans can't read. Values are the byte stream, so the values are what the data is. And it supports multiple backends. So we also created the POSIX backend because that's what we run today in operations. But we are developing a DAOs backend. So Intel DAOs is a distributed asynchronous object store, a bit lower level, domain agnostic. You may want to have a look at that. I think it's very promising. Also, a backend for Ceph, which is more cloud suited, and of course, as I said, it's driven by a semantics language that the user is familiar with. It's transactional, asynchronous, consistent, immutable, versioned, uses rendezvous hash on the background so that there is no synchronization needed across servers. And in this project, we actually obtained very interesting performances. So this is application measured performance. So this is not hero numbers. These are really how many bytes did that transfer over how many time with a wall clock, right? And in this particular project, we were with this particular hardware, with 16 server nodes, we were able to demonstrate 72 gigabytes per second of sustained per second of application throughput. This is IFS writing to it at 72 gigabytes per second using 16 nodes, right? By comparison, just to give you an idea, today, if we do roughly 40 gigabytes per second on our Lustre file system, which contains 280 objects, OSTs. So it's an order of magnitude different in terms of hardware involved, and yet only half of the performance. So the FTP parallel read performance, we obtain 60 gigabytes per second. Of course, the performance of read is a little bit lower because, of course, we have to find the data. You ask for temperature, we still have to find where temperature is. We have a good indexing system, but it takes its time. So we were quite happy with it, but we're really, really happy was when we actually used this to run a forecast with model, IO, and PGen all together and demonstrate with that there was no effect at all on the runtime. So if you run with Lustre and a proper Lustre system with model with IO, then you add PGen, you see again the slowdown from 1700 seconds to 1900 seconds. But when you run with this object store and this technology, you saw that actually not only we run faster, but with the project generation does not seem to affect at all the model when it's run. The coupling that existed is gone. So I think not only this hardware, but this sort of software is very important for the future. So FTB is currently operational at ECMWF. It's open source, it's available, and we have a publication if you're interested to know more details. Another thing we have been investing a lot is into this multi-IO server. So it's IO server that is coding in the development at ECMWF, was sponsored by this Maestro project. We have completed the full adaptation of the NEMO model that we use inside of our Earth system model to use this, and we'll soon also port our atmospheric model to use this server. So basically, as our previous speaker was describing, we have a series of compute tasks that do an end-to-end aggregation using synchronous MPI calls into IO server tasks that will do the part of the encoding of the data, computation, and IO. They also we are also adding compression for this tasks. So it's also part of that. And of course, when we're done, we write that to persistent storage, which happens to be the object store that I've just described before. So what's interesting about this IO server is what we are introducing completely programmable pipelines of data processing within the IO server tasks. Okay, so it's a generic user programmable actions that allow you to say, okay, when you see this data passing by, please route it this way. And when you route it this way, please do this action on it, do this statistics, do this aggregation, do this, write it there. Or so in a way, it's a routing system for the data, and at the same time, acting on that data, that data as it passes through the system. It's also designed to be easily extendable with new domains, with new grids, for new models. So in particularly, the NEMO model has a different grid than our atmosphere, than our wave model. Just that there, you have 3 different types of grids, 3 different types of structures. It's structuring grid agnostic, basically. So one of the things we are introducing into this is the possibility of doing on-the-fly product generation. So product generation at ECMWF is user-driven. So users tell us, please make this product for me. Nowadays, this is a bit of a ad hoc system where the user does that. We wait 24 hours, and the next day the user will, on the next run of the forecast, we will have reconfigured our pipelines, and the user will get its products. But now we will do this on the fly. So when the model starts running, we'll read the user requirements. The multi-IO server will compute all the pipelines and all the directed cyclic graph that needs to be in place to generate those products, and then we'll create and disseminate, and we will send that to dissemination. So this is something we are actually currently developing and researching in this Across project that we are sharing with the MPI and the KRZ. So all this, the advantage is all this will be done in memory. So where the data is located, so we don't wait for the data to get into storage in order to process it and so on. So we believe this will be a big game changer to be able to do and handle the data at such high resolutions as we are planning for this NHR. Finally, another thing I would like to mention is that part of this digital twin engine, we will also going to go to start providing an API for accessing our data with hypercubes. So weather forecasts are hypercubes of roughly 6 dimensions, as you see here: longitude, latitude, multiple variables, including atmospheric levels, or in physical parameters, time steps, and probabilistic perturbations. So every day you could consider a forecast as a 6D time cube. And of course, these grow quadratically with resolution, as you very well understand. At 1 kilometer, we estimate destination Earth is 1 petabyte. So imagine a 1 petabyte hypercube. And so the problem here is that each user wants to access it in a different axis, right? You have people wanting to do statistics over perturbations, vertical crosses, cuts in terms of vertical atmospheric levels, or just plotting things on a time series, for example. And we need to provide the access that is as fast as and low latency to every axis as possible, not have preferential axis. And in doing that, also reduce the amount of data that we have to give to the user. I don't want to send the whole hypercube to the user. I want the user to come and tell me, I want this. I will extract it from the hypercube and I will send it to the user. The idea is that we're trying to change slightly the way we see the workflows. Okay, yes, you have an HPC that is the big producer of data. Yes, the HPC will put the data eventually to the parallel file system. And yes, we will also archive from there to a more persistent storage, for posterity. But meanwhile, we will create a location where we can put temporarily for let's say the next days after the forecast, the hypercube in a low latency system. Maybe, who knows, we can have a system like with these NVDIMMs as I showed before. And in there, we will give a better access to the user by providing ways that the user can extract the data, just the data that it needs on the axes that it needs. And hopefully, we also, at the same time, deploy this close to maybe in-premises cloud where users can come in and use and do their workflows as close as possible to the data as we can. For doing that, we are really researching into how can we do this feature extraction. So basically, this is a little bit of computational geometry here and maths at a very high dimension. So you think of it like a query of a user is a polygon in multi dimensions. That's actually called a polytope. That's the name we're giving to the software. So this polytope is a query that you intersect with your hypercube. And so imagine your query could be a 4-dimensional polytope, but you want to intersect it with a 6-dimensional hypercube. And then as a result, you have these extractions, which are hopefully much smaller than the hypercube itself. So these extracted data, we then repackage it and we send it to the user. And the user gets access to just the part that he needs. And we are trying to make this, and so far we believe we will be able to do it as generic as possible. So say if I want, say, Germany just for the next week, I can describe that in my language, and then I can ask for that, and I do a cutout of only that area for that time frame, and I only give back that to the user. So this is something under development. So stay tuned. I hope we'll be able to show you soon. So messages to take home. Yes, ensemble data sets are growing quadratically to cubically in size, and it's really a challenge, especially if you want to run time-critical applications. We are engaged we ECMWF are engaged in building a kilometer-scale digital twin for weather extremes. And in doing so, we are adapting to a more data-centric view of exascale weather forecasting, exploring in-situ data analysis and hypercube feature extractions. And we are also refactoring our software stack end-to-end to enable these exascale data sets. And we are providing this as part of this Destination Earth digital twin engine. And everything we will be doing will be open sourced and available for the community. Thank you very much.
Right, we have a few questions on online on a Google document. We get a first question from Suvi. Does one need specific hardware with NVRAM DIMM to use FDB? And how does FDB differ from other popular key value stores like Redis? And why did you decide to develop yours?
Very good question. No, you do not need NVDIMMs for FDB. We were just demonstrating it that you can use whatever backend. So the FDB can run on a simple file system, right? On your parallel file system. In fact, that's how we run it in operations today. Why did we do FDB? Well, actually, we already had the previous version. This is the 5th version of the FDB. We already had it. Why don't we use an off-the-shelf key value store? Because the FDB talks meteorology, right? It's a domain-specific object store. It talks Earth systems, if you want. You say temperature, and it understands temperature. It indexes the data, and it will retrieve what the user wants in the language of the user. It's not, you don't have to translate things into strange keys and give the user strange keys that the user then remembers and comes back and gets it. We could make a backend of the FDB on top of Redis. Redis is a technology. If you want, the FDB is a kind of a translation layer. I think that there's more we are doing. We are doing a distributed object store. We are ensuring consistency. We have, from the point of view of our time-critical applications, we have a few requirements, and it's not easy to find something off the shelf that meets all those requirements.
Thank you. We got another question online. Nikolai said most of it is grid-based, but Destiny aims at the climate community. And what are your solutions to get the data to NetCDF in the end?
So, okay, I think there are many things here to mention. So, in Destination Earth, it's not the Destination Earth is not targeted only at the climate community. It is including the climate community. So we are providing these as APIs to store data. Now, data internally can be stored in any format. If you use zarr, for example, internally it can use different formats. And I think NetCDF is a format to give the data when it finally reaches the user. Internally in the system, the data can be in whatever form. So I think NetCDF is part of it, but as a delivery to the user. Internally, we can choose whatever form. The FTB, by the way, is currently using GRIB, but it's not bound to GRIB. It's internally you can store any byte stream. Okay, you can store. For example, we use the FTB also to store observations. Okay, so anything that has a metadata that identifies the data and a byte stream that you can store as a byte stream, you can store inside of the FTB.
Thank you. We got one question in the room. Sophie has a question.
Yes, the functionality of your I/O server looks very like XIOS, indeed. Beside maybe the format in which the data are produced. So, can you say a little bit more on the difference between the XIOS server and your FDB server? And did you look at XIOS at the beginning? And if so, why did you choose not to go with it?
Yeah. So the reason why you also need to understand that before we had this I/O server, we had another I/O server inside IFS. So IFS has its own I/O server, which is something developed by Meteo France, and its architecture is the one we are following. So multi-I/O, if you want, is a rewrite, a more extendable rewrite of the I/O server we already had inside of IFS. XIOS actually came after, and after that I/O server that we had inside of IFS. So there are similarities. The architecture is not too different. There's one thing that maybe is different, which is what inside of our multi-I/O I/O server we do is that we don't understand the data. The data is just passing us messages, and we route the data around based on the metadata that is attached to that data, and then you can put it, for example, to the FTB, or you can send it to dissemination, or you can send it to your archive. But in the end, the data is you don't have the concept of a file like XIOS has. XIOS at the beginning, we even have a workshop at ECMWF with the previous presenter, where we discussed the similarities and the differences. And the problem, well, our difficulty was that XIOS was extremely bound to NetCDF. It was very much bound also to this XML form, and we wanted to be able to have this already from the very beginning of our design. As we were rewriting our I/O server, we were really looking at these programmable pipelines. The way of really allowing the user to inject into our pipelines whatever the user wants, such that we can do our post-processing inside the pipelines that are inside of the I/O server. So for that, I mean, I'm not saying that it's completely different, but there's say a 50% overlap with XIOS.
Thank you. I think we're going to go into the coffee break now. We're probably going to take a bit longer for the coffee break. I think we're going to reconvene at 11:15. Right. So now we're going to the last three session of the three talks of the session. So we first have Grenville Lister from NCAS, who is going to talk to us about the ExCALIData project. Thank you, Grenville.
Thanks, JC. Thank you for inviting me, giving me the opportunity to talk about this project, which is kind of fairly new. So this talk might be a slight departure from previous talks, which are detail-rich and results-rich. This will be a very kind of quick skim, high-level view of what we're doing. Hopefully, you come away with an idea of that, and to give you some indication of just kind of the progress that's been made so far. Here we go, the usual thing, we have the branding. So this is a project which comes under the Excalibur heading, which is kind of Met Office run activity, or it's kind of UK science-wide. Our partners are DDN, Stack HPC, University of Cambridge, because we're the University of Reading, and NCAS. And I'm talking here, but it's important to say, I think, that the project is, Brian is the PI of the project, so and there are many people involved. I'll try and indicate as we go through who the people are, because if you have questions, I might be directing you to those people. I'm just the one doing the talking at the moment. So it's all quite a new project. There's a site there which is sort of well worth a visit. It's again fairly high level, but that will give you a very good view of the scope of the project, which is much. It's much wider than that. I think you'll recognize from what I'm going to talk about here. So just a few words on the kind of high-level Excalibur itself. What does Excalibur mean? Well, Excalibur, that's the description there is exascale computing algorithms and infrastructures benefiting UK research. That's a sort of tortured that to get the word Excalibur out of it. And so I guess we should not concentrate on the UK part of this. The project will deliver open source software. The results will all be completely open to the whole world, whole community. But so it's a program which is it's been going on for a few years now, since 2019, and it'll run till 2025. And to basically recognise that there needs to be a kind of concerted effort to redesign some of the high priority computer codes certainly run by people in the UK. So so there are principal areas which the program concentrates on, and I'll mention that a little bit more in detail also. But of course, it's got pillars. I guess we'll have pillars. So three of those pillars: the separation of concerns, co-design, and data science. I think they're kind of no-brainers. You'd expect those to be there. But what's refreshing, I think, is the recognition that we need to invest in people. I think we all know that scientific programmers like hen's teeth, they're really hard to find. We really struggle to keep them in the business. So there's a kind of a work package to try and ensure that we're investing in the people and kind of developing the research software engineering community in the UK. And we'll mention that a little bit more as we go on. Okay, so that's that. So clearly there are themes, there are always themes, and they break down into kind of 5 areas. In principle, in no particular order, I don't think, but the high priority use cases have been identified as weather and climate and fusion. So because we're principally involved in the weather and climate, but one of the requirements of a successful bid was that your proposal needed to have a partner in essence in the other field. So all our work will be with regard to climate modeling and weather prediction and the like, but we also are working will work with the Turbulence Consortium, who have a project to look at, I guess, flow around turbines for energy generation. So while that's not fusion, the Turbulence Consortium certainly are closely involved in that activity. So we had some interesting discussions with the people in Turbulence Consortium, and clearly their problems, the problems they encounter are very similar to the problems we encounter, that we all encounter running on HPC. Perhaps not so critical in the data cases. I mean, they clearly are a little way behind, I think, in their application of metadata and standards and the like. So I think we will have something to help them with in that regard from this activity. So that's a good thing. So it's not only about these high priority cases. They've all recognized that there are technologies, there are requirements in other areas that will use high performance computing and need some algorithmic development and some help. I guess biomedicine is, we all know that one, but recognition that these things are important in social sciences and humanities, I think, is also quite an interesting aspect of it. I'm not sure how. It would be interesting to know how we could help in that area, but that's for another day, I think. We can't do any of this without have access to hardware and software necessary. So there's a whole theme on test beds. So and we'll be using a test bed, and we'll mention that a bit later on. So this requires this sort of addressing the issue of early access to novel hardware and software. I mean, we need this stuff to run on, to test the ideas and come up with the and apply the algorithms on these new architectures. So the current hardware is just kind of not the right place to do it, and there's not the resources available really to do that kind of thing. So that was good. Cross-cutting research, I think that kind of speaks for itself. I mean, that's the area that's the theme that we were successful in. So I'll discuss that more in detail. But then there's also this RSC knowledge integration. So RSC is a term that we use all the time, research software engineer. So the idea is to grow this interdisciplinary RSC community to identify the skills gaps and identify ways to fill the skills gaps. So that will involve a kind of a training program, at least a training program, and more. And we've sort of addressed that in our bid, and we have to address that in the bid. And so I'll mention a little bit about that too towards the end of the talk. So I'm rushing a little bit here, but because I have a time constraint that we don't in the program. So the part that we're involved in was in the cross-cutting research, and there were four areas. There were four topics that were open for proposals: I/O and storage, data workflow coupling, domain-specific languages. So we weren't involved at all in coupling and domain-specific languages, but we thought, and I think we do have a lot of experience in the I/O storage and data workflow. So we applied to both of those. So I/O and storage, that's sort of that's fabric. We want, as a group supporting the climate community, we want the models to run as fast as possible. We have finite resources, we have finite compute time, and we have finite space. So anything we can do to improve the performance of the model, that's great, and to reduce the storage required, that's great too. So speeding up I/O, that's one area, definitely. Improving the efficiency of storage, that's certainly an area. So there's a compression aspect there, possibly. Finding out what's in storage, I mean, we all have that problem. So that was a problem identified in the Turbulence Consortium. They do their simulations and they put the data in storage, and then 6 months later you barely know what's there. So I think we all have had that problem in the past, and we certainly still have it. So part of this bid addresses that issue. And then the data workflow area, that's involved with, for example, minimizing movement of data, minimizing production of data. So I'm thinking in terms of ensembles here. I mean, our increased interest in ensembles is going to make life very difficult unless we somehow think about more strategically and carefully about the kind of the the data output that the models are going to create. So so again, I mentioned that. So we were successful in both of those bids, and we created, I say Brian created this thing called ExCALIData, which was a combination of the I/O and storage and data workflow bids, and we named those individually ExCALIStore and ExCALIWork. And so ExCALIStore, that's principally a combination of work done at Reading and Cambridge, and that's the kind of fabric issues, and data workflow ExCALIWork is in combination with Reading, and we have partners in the commercial environment, DDN and Stack HPC. And I'll mention those also. So I got a picture here, which is kind of the thinking, which kind of describes the thinking behind the whole bid. The picture was a vertical slice originally, but I couldn't get that on the. So just follow the arrows. So I guess the idea, and we all know it, is that the data in the workflow in your model will in a model integration or a simulation will start in deep storage, and ultimately will end up in deep storage. So how do we even know what's in deep storage? I mean, what is deep storage? That would be different potentially for different institutions, different HPC environments. For us, deep storage could be tape at Jasmine. It could be on disk at Jasmine, depending on the kind of simulation that's been done. It could be on the SGF node, for example. So there's an issue about knowing what's there. So this project kind of tries to address that issue a little bit. So that involves standards, metadata, and to some extent, okay. So I don't want to retrieve every single bit of data I've got in deep storage. I might just want to do what Tiago was talking about, which was just kind of retrieve a slice of data. So then there are tools that we're developing to do that kind of thing, and we'll talk about that a little bit. Okay, so when you've got your data, you want to run your simulation, and some of the issues here we won't address. We won't address things like parallel reads, but we certainly will like to address the idea of in-flight producing in-flight data, in-flight statistics generation, and for example, in ensembles is what's in the back of my mind right there. So that's so we want to write data quickly. So that's that kind of the synergies there with across the project. So we'd like the fabric to be as good as it can be, and we'd like to write as little data as is necessary for the particular simulation. If you insist on all your ensemble members writing out all the data, then we're sort of stuck. But nevertheless, I think there's scope for not doing that. I/O servers. We're interested in I/O servers. Of course, we're principally using XIOS in the work we do here. We're also interested in middleware. So we have a part of the project to kind of investigate AIOS and ESDM. I'll just mention those a bit briefly, because we're interested in compression at some point down the line. So the model writes its output, and then we have to do something with it, like to analyze it. So that might mean dropping back into deep storage to get some more data, because typical model analysis isn't just analyzing the data from the model. It requires comparison with other data. So again, there's the standards and the formats and the conventions and the metadata issues right there. And there's a whole bunch of key problems there, but the one that we kind of concentrating on in this project is the final one, is the active storage issue. And so that would be a sizable component of the workflow element of the project. So we'll mention a little bit more about that. And then we're going to write data to store. We want to compress it. We want to understand what's there. We need to sort of catalog it, and we need to be able to shard the data across several storage media, for example, possibly. We don't necessarily want to write single files. We might want to break it up. So we sort of going round the houses a little bit here. I mean, in the old days, the UM used to write out a single file from P0. Okay, we got away from that. I mean, Nemo went right away from that, writing out a file per processor, and we've sort of come back a little bit with I/O servers to write possibly a few files, and so we will have a few files in output potentially. So then we need to understand where they are, how to understand how to move those files, for example. That might be one thing you'd like to do. How we can slice data out of those files, how we can put data together in a kind of a sensible way. And we'll mention that a little bit too. I feel like I'm fast running out of time. Okay. So a little bit more detail about the XCALI Store project. The idea is, I hate to read things out, but I'm going to do it anyway. Development and demonstration of novel approaches to optimizing aspects of the data flow to improve I/O for large-scale applications. So the kind of main elements are storage interfaces. That's how do we see our data? We could be, as I said, spread in multiple files, possibly over different storage media. That's one element of it. How do we manage that data across the storage tiers, and possibly between institutions? So the idea of moving lots of bits of data around is something which is kind of exercising us. Then there's the accelerating I/O, which is the kind of improving the network fabric. And I think one thing that this is principally the Cambridge element of looking at this. So there's a particular element here looking at RMDA and those smart NICs. So, and an important part of all this is the development of advanced burst buffers, and that work is going on at Cambridge too. And I have one or two words to mention about that. Then I mentioned briefly that we'd be investigating some I/O middleware, principally ADIOS and ESDM, and we have little experience with ADIOS, certainly a little bit more experience with ESDM with Julian. So we really need to apply that to the use cases, to a climate weather use case potentially, and a fusion use case, and so that work will go on, and that work will happen on the new network fabric that Cambridge have developed. And then, of course, we'll be running synthetic tests and ultimately the overarching application to weather and climate use cases. So this is drilling in a little bit more about a couple of the aspects that I've kind of mentioned there. So in terms of the kind of interfaces, so this picture's a bit small, I appreciate, but there's a couple of elements in the project here which basically come under the heading CF aggregation and CF store. And the CF aggregation, which you may have seen this because CF aggregation has been going on for a while. I think probably cross-cuts several projects. But the idea is that our data lives potentially in multiple files, again, and possibly on multiple media sources. So here's an example of what CF aggregation would do. As a user, I don't really want to be bothered with all these files across multiple media. I just want to know, I'd like to use something which looks like a single file for my data set of my, I think what's been coined atomic data set, potentially. And this is an example, for example, where we have data which is spread across two files because it's a time series. There's part of the time series in one file and part in the other. But as a user, I'd just like to see the entire time series for the year. And what CF aggregation does is it will create rules and a set of information and metadata so that you have an aggregation file. But as far as you're concerned, it's one file that represents my entire data set, and then the aggregation understands when it needs to access the data, it understands where the data is, it can go and grab it and pull it back when it needs to pull it back, and so that the user can effectively just see a single file. So the aggregation rules, I think, are quite comprehensive. If you'd like to go read about them, there's a link there. So you can aggregate over time, you can aggregate over spatial dimensions, you can aggregate over several other things which are described in detail in that document. So that's an activity which I think will bear fruit, certainly. And yeah, so it's been developed. There's also some development for UGrid. So that the whole thing's kind of going forward in the way that you would expect. And then, so the other element of this is the idea of knowing what what data I have on where, what data I have where. And so there's a piece of software being developed here called CF Store, which will help you do just that. Basically, it'll allow you to know what you've got where. Hopefully, it'll allow you to moving bits of data between storage elements. I think that will be an important and useful future activity. It certainly will. I know it will be. So the people, I put some names down there for the people principally involved in these activities. So just for reference. More working on Sky Store. So I mentioned that there's the fabric part of it, and the picture here is probably an out-of-date picture of the Cambridge research computer system. I know it's out of date, but there's another. It's a significant component on which we can test some of the ideas that we're developing. So the reasons I know it's out of date because going out of order here, they've just built a DAOS prototype system, which will be part of the research environment, and I think that's they've been testing it at some with synthetic benchmarks, and it's proven to be, I think, pretty efficient. So that's ongoing. They're also very interested, and they've been working hard on developing this burst buffer technology. There's a couple of things I've just dragged out of a report here. So just to say what's been going on with them. So I guess one thing that you need to do with the burst buffer is you need to stage the data or destage the data rapidly as possible. So I guess they've improved the staging destaging process simply by using some different utilities to do that activity, and there's a little plot down there to show the improvement in performance. They've developed some slightly different lifetime cycle management, so by deploying per job file directories rather than file systems. So that's the bullet point. And development, I think, will include use of Slurm and Luar functionality. I confess I'm not familiar with Luar. I did look it up, and so that activity is ongoing. So then, in principle, I think they put the burst buffer stuff on top of this DAOS prototype system, and hopefully would benefit from both developments and technology there. And again, there's some people down there who are interested in developing that project. So shifting gears a little bit to the other project, the XCALI work, I'm going to read this again. Development and demonstration of novel approaches to taking certain computations, and I can't read the next bit because my screen is hiding it. Reduce the need for data movement to improve I/O in large-scale applications. So this is the Reading. I'm more familiar with what's going on in this because most of it's happening in Reading. So the idea is to move the computation away from the traditional analysis phase. So and increase the concurrency and reduce data movement. So I mentioned before the active storage idea. So I guess the idea here is that you have a lot of compute in the storage itself. So we'd like to monopolize to take advantage of some of that compute capability to do some of the reductions that you might need in your typical kind of application. So I think the goal here would be to do decompression on the fly, to get the storage to do the decompression when you make the request for the data.
Grenville, 2 minutes, please.
2 minutes. Oh gosh. Okay. Okay. I'm going to rush through this now. So that activity, then there's the ensembles. So leveraging XIOS capability. So in the current model and in Elfric, and again apply them to the regular tests. So I'm just going to mention here that the active storage, currently we're concentrating on the layer between where the line is drawn there. So the interface between what's going on, the software required in the storage itself, and the software required by the user at the higher level. So that it's all early stages. People are thinking really hard about what the interface should be and what the API should be. So I'm going to skip really fast now, and I can skip this picture. It's not necessary. So we've been working on XIOS and ensembles for quite a while in the group. We've been successful in setting up an atmosphere-only ensemble. We recently extended that idea to a couple model ensemble. So this picture is just a representation of the kind of communications in the model. So there's Oasis communicating between the atmosphere and the ocean models. There's that's a little grey box, and there's a little red XIOS client on each of these individual elements, which they're kind of communicating with the XIOS server. And the XOS clients communicate with each other in order to do the ensemble statistics. So I don't know if for those of you who are not familiar with how this works, in its simplest form, you simply define an ensemble axis. So in the little bit of XML here, the first part defines a grid, and attached to the grid is the idea of an ensemble axis. It's the number 1, 2, 3, 4. In this case, 0 to 3 or 1 to 3, 0 to 2. And then in the you define a target grid on which you want the output to come, and XIOS allows you to just specify a reduction. In this case, it's just an average. So just by doing this, you can get the ensemble average of whatever, in this case, some kind of I don't know what that field is. So we've recently just got this working through some very, very timely and useful discussions with Jan and Sophie to kind of put us on the right track. So this actually now works. So so we're really interested, excited about getting this, getting some performance tests on this and applying it to some real use cases, which we have plenty of those in the offing. So very briefly, there's a kind of a knowledge exchange element, which I guess you'd expect. So to ensure that we have integration across the program activities, so that's across the Turbulence Consortium in the near term for us, and possibly in the wider in the larger context. And so I'm not going to go through this diagram, but we have, I think, a fairly comprehensive plan about how to do this to keep everybody involved and up to date, and to share our knowledge and experience, and to kind of bring in whatever comes from the other side of the interaction with the Turbulence people also. So, yep, that's it. So, yeah, sorry, nothing fantastically concrete. We're excited. This project is going to produce some really good results. So I ask you to watch the space, and thank you. Thanks. I can't hear anything now.
Can you hear me?
I can hear you, but I'm not streaming the...
Well, if you can hear me, I'll look at the document. But there was one question of me that Brian already answered, which was about the compatibility of the CF aggregation convention with unstructured grid. So Brian provided an answer on the Google Doc, so people can have a look at that. I don't know if there's any question in the room. So I have a question. So there's a lot of there's a collection of a lot of tools there, which is great, and a lot of things can benefit the community. But do you look a bit at the whole workflow view? Because there's a lot of layers in the workflow, and we can optimize something that's not on a critical path. So do you look a bit at tools that look at the overall chain and see where really are the bottlenecks in the workflow and the storage?
Not specifically, JC. That sounds like a whole nother Excalibur bid. But I mean, yeah, I don't know how to answer that other than say not specifically. Indeed, we are interested to know where those particular bottlenecks occur. We think it's not necessarily the bottleneck. It's reducing volumes, for example. So that's so writing out the entire ensemble rather than writing out the ensemble statistics, I think, it kind of sort of addresses that, but not in the way that I think you're requesting. So no, I don't have a good answer to that. We don't have that tool at the moment.
That's great. Thank you. Thanks again.
Thank you.
So the next talk is from Gabriela Aznar from MSwiss.
Hello. So I will start. I'm Gabriela Aznar from MSwiss. And today I will explain you the work we are developing about access to gridded data using zarr. I guess I have to put the button now. No. This is not mine. This one, yeah, thank you. So let me start with the motivation, why we went into that field. So in my group, we are dealing with post-processing. We do that to enhance the numerical weather predictions with our own observations, radars, to make also tailored custom specific products for policy, decision makers, civil society. So one example of a typical data science application we might have is this downscaling, as it was mentioned also for machine learning applications during the first day of this workshop, where my colleague Daniele Nerini, they took the Cosmo model at 2-kilometer resolution together with a demographic model of 50-meter resolution and observations, and obtain a quite accurate wind speed field at 50-meter resolution. Only to generate that, he used about 100 terabytes of data, and with the current resolution of our models, the variables we were using here, surface fields, this means an increase of 35 terabytes per year with this 1-kilometer resolution. And it's not just about the amount of data we are dealing here with, it's also about the heterogeneity. So we are dealing with data from different sources. At this point, we thought it might be clever to think about some solution to make our life easier on how to access that data. So that's why we came into this unified access API idea to fit our data pipelines. Let me explain you a bit how we want to execute the things in our group, well, and probably just MSwiss also. So on the one hand, we have the production environment. This is currently now a Kubernetes cluster, where there we are doing the post-processing, different post-processing types of different complexity types. Might be just easier extraction and multiplications, or something more statistically complicated, or also the inference part of the machine learning methods. So for that part, we will just typically need only some days of data to make this. So the last days of the data. On the other hand, on the development side, there we need much more amount of data, of the order of years. And here, what we want to do in the development environment is to be able to efficiently analyze all this amount of data, train our models, statistically in machine learning. And we are planning to do that also in an HPC infrastructure. So we are currently building a Kubernetes cluster as well at CSCS, which this will allow us to easily transfer the methods we have trained between both environments. So the portability of our methods should be quite straightforward then. To make all this work, as you see, we have planned to have this data store with a unified access API to the data, which we called GridFX. And there, it's not just about copying data again, it's about maybe putting also pre-processed data that we will use and we have to access continuously to train our models, or maybe also data we generate, like the features of the machine learning. Exactly. So as you see, we want to have this graphics to fulfill many of our use cases. With this in mind, we thought that graphics should have the following properties. It has to be cloud native so that we can access it from our services in our Kubernetes cluster. And also, this allows us to deploy it everywhere that we will need. It might be at CSCS, where we currently have also our Cosmo models being produced, or maybe at the European Weather Cloud. And then we can access it from everywhere. It needs to handle multidimensional arrays efficiently. For that, we thought about using compressed binary chunks, and that's why we chose the zarr specification. Of course, the idea is also to offer us, to the scientifics working with that data, a unified and semantic data access. This means that you don't need to know what's the name of the variable for air temperature in the radar data and in the observations and in the Cosmo model or in the something else. We are using CF standard variable names. And you don't need to really know nothing about the original file structure of the data. That's what I mean with semantic. It's nothing more complicated. Also, as you have seen, what we want to know in the operational environment is to have the latest data, so we should be quite efficient by importing data, also writing and also deleting data. That's why we are implementing here a rolling archive. And then also we want to have, like, as I said, efficient handling of the data, efficient loading, and also be able to slice across any dimension through the data. That's why we chose here to follow the Pangeo stack using Xarray Dask together with zarr. And finally, we have also developed services, web services, that these ones are the ones which will enable us to build event-driven architectures, and also to offer language-independent access to the data, because of course we are focusing a lot of Python, but we have colleagues also working in R and these things. So, talking about this event-driven architecture, it would look something like that. You have the data which is being published, then you have the event broker, which tells our import service to take the data and put it into our data store. Then you would have the users, which are subscribed to these events, and then they could use either the Python API or this export service, this data service. On the other hand, you also have the catalog service, which offers you access to all the metadata so that you can see what's actually available in the data store. So let me now go a bit deeper into the details on how this works. The data model we are using, it's very familiar for all of you who are familiar with NetCDF and Xarray. We don't really want to reinvent many things, just use what exists there. The only thing what we are enforcing here is to use the CF naming convention, so the variables need to follow that, and also the coordinates. And then for the attributes, we keep them as key value, and we also consider that we might have nested dictionaries of attributes, as you see down left, where you would have attributes which are time-dependent. What we enforce is to have two kinds of attributes for this data set. So the data set is a set of variables with common coordinates. And these attributes that we enforce to have are the source, where the data comes from, and some tags. So we label the data sets so that we can then access them and refer to them when we want to use them. From the data format, this looks like follow. We have organized the data using zarr this way. So on the top of the hierarchy, you have the source group, and then you have just besides the what we call the gridfx array. So this is an array which is identified by a UUID. You have attributes where, for example, you have the tags which identify this array. You then have a group for the coordinates, which just needs to be once, so it's a known group. And what we have now, it's then a group pro timestamp. So in case of model data, it would be the forecast reference time. In the case of observation data, this would be the observation time. And in every timestamp, you have the variables that were provided or that you were interested. So it might be that you don't have the whole variables for every timestamp. And every variable is then a ZAR array. So you would have many of these arrays, or maybe also the one which is below, which is just about static data. So you don't have the time axis splitted in the group. The reason why we have time axis group is to make this rolling archive strategy more efficient. So this way you can rapidly see which was, for example, the last timestamp that you are interested in, which are the timestamps which are more old, you just delete them. And of course, the static data provides you more freedom on how you want to chunk your data. And then what we do also, it's operations between the X arrays, between these ZAR arrays. So you can also concatenate arrays which have the same tags, for example, to obtain an X-array dataset. So what we do internally, each GridFX array of the ZAR specification, it's converted to an X-array dataset, and then we can concatenate the datasets to generate one dataset which share the same tags. That's what the user is expecting, actually, when they refer to a tag. So this use case, it's when you would have like these variables and different coordinates. We organize that internally in different GridFX arrays. Okay, well, you might not need to know all this. It's quite simple, the concept, but what you have seen was now the metadata view. What we have done is to split the metadata in the chunk information to make it more efficient for the following reasons. So using the metadata store with Postgres, you can get fast catalog queries, so you can see fast what's available there, just by SQL queries. You can also identify fast what's the data that you want to retrieve. Like in these use cases, which runs in operations where you just want the last timestamp, you can identify very fast through the metadata what's the last timestamp, and then you just downloaded it. And the nice thing about using Postgres is that you ensure the consistency using transactional operations. So until something is not committed, you can always go back if something fails. This allows us also not to have to consolidate the metadata, which is quite expensive for an archive which is being updated all the time. Okay, and then for the chunk store, we use here S3 for this cloud-native requirement that we have. For the metadata side, we have also made some further thoughts on how to obtain more fast the data we are looking into. So for our regular queries, we would have the ZAR nodes table, which is the view I showed you before with all the data organized as I showed you. But then we have lookup tables also to get some queries faster for storing so information where the variables are stored and the coordinates are stored. So we did here quite a bit of work to adapt this metadata store to our data format. And we wrote, so we had to write a class which inherits for the mutable mapping class, where easily then you can use that together with ZAR. So here I've told you a bit that we were using class. We are doing all this in Python. So this is how it looks like, all these APIs. We have on the top, on the bottom, we have the GridFX database, which is split into the chunk store and the metadata store, as I just explained, using ZAR. Then we have, you see this GridFX library, which is written in Python, which is the one which makes you this logic between the ZAR and the X-array datasets. And then on top of that, we have an export service. The export service I referred before with this web service. We build it on OpenDAP so that the people who use it is quite familiar with NetCDF, so they can just use it as NetCDF. And we have then the import service, which is the one which uses the writing functionalities of the GridFX library. And the import service is defined as a set of functions which implements the logic on your data set, how to map it to this GridFX data model, and then uses the writing functionalities of the GridFX library. The import service is triggered by this event pipeline I referred before. And then finally, we have also on the bottom right, the catalog service, which makes directly queries to the metadata store to see what's available. And that's quite efficient. So here's some example of how this works now. You have, with a Jupyter notebook, you can refer to your Discover service. So yeah, here is with Python, but you could use it with any language. The fact that it's cloud native makes it also very easy to scale it. So more processes we have, we just need to use one pod more. And well, here are just some examples. Like you would ask, if I'm interested in these variables, which sources do I have, which provides them, which details of the source you have here, like the bounding box or the reference system. And then you also might be, well, what you will need to know also is which timestamps are available for those variables in that source, which would be the last query. So once you know which variables, which timestamps are available, you're interested in, you can use the APIs. So in the Python API looks something like that. You would instantiate the GridFX database with the metadata store and chunk store credentials, basically. It's the information you need to provide here. And then you would give like the source, the tags, the timestamps, which might be a range or a list, and the variables you're interested. And you just, with a call, you would get the data set. What you obtain here is the Dask array. So we are relying on this X-array, Dask, and zarr frameworks. So currently, we are using Dask in a single machine. So if you use that, you will use your own, the memory you have available in your own machine. We are also looking further into that. But this is the use case we expect to use in this development environment, where you want to efficiently deal with big amount of data, because here you have the data chunked. You should be able to do efficiently all the operations you need to. And then for more thinking about the other use case, where you just want to have the latest timestamp to make your predictions, you can use also the web service. It looks something like that. Again, we have a cloud-native service. It's easily scalable. Then you provide, again, the same data as before, source, tags, timestamps, and variables. And you get an X-array dataset again. The good thing about OpenDAP is that you can here have, again, the lazy loading. So when you see this view of the dataset, you haven't loaded anything yet. You just see the metadata information. Then you can just maybe slice across any dimension you want and just also do some operations, like here the mean value across the dimension realization, which is ensemble, and then just load that. So that's also efficient. Okay, so that's how it looks like. We have been developing this data store and services around it to offer a unified access to our multidimensional data. So we want to use them to trigger our event-driven architectures we are building, but we also want to have efficient data loading and manipulation, and we do that through Dask. Of course, there's still a lot of work in progress still. I'm sorry I couldn't show you metrics on how well all this performs, because we are not there yet. Currently, we are working on making everything asynchronous what we can, like the PostgreSQL database calls. This has to be everything which doesn't involve zarr, because zarr is not itself asynchronous, which also makes sense because we are using Dask on top of it. Another thing we are very interested to look into is about using Dask distributed on several machines and not in the local machine. That will be very interested also in the Kubernetes cluster to be able to generate pods with these task clusters only by demand. Like that's a very interesting use case, and I know already that the European Weather Crowd and Dask have made some progresses on building this kind of infrastructures. We would be very interested to use that. And then, as I said, we still have to look into performance. Like, we know we have put some efforts here on how to handle the metadata and all this rolling archive strategy. We still need to properly look into what's the performance impacts on using these structures, but we are confident we can adapt that for our needs. For example, using this static data instead of the timestamps groups if we want to deal efficiently with big amounts of data. So we have to fine-tune it for our different use cases, and it might probably be just the case that for different data sets you might want to choose between the different chunkings that you might need for that case, which is quite easy with zarr to handle with because the rechunking is quite straightforward. Okay, and then also another issue we want to look also is how well it behaves if we start doing this store big and big and big. Maybe we need to split it in different buckets on ENES-RI or in different zarr structures. So yeah, these are still things we are looking into. And that would be.
Thank you very much. I think there is a question, but it's still writing, so I will do mine. I have, or is there any question in the room? Like, no. So waiting for Sui that is finishing. So
actually, I can also say, what's the data service like? Is it OpenDAP or is it threads or what's it written in? It's like Python. Does it have computability, like do aggregations in the backend or? GridFX service, I meant. Yeah.
So you mean the OpenDAP layer we use for serialization, right?
The service itself,
yeah,
which gives API and everything. Just curious, what is it written in?
So we have written our OpenDAP Python ourselves, but of course might be more efficient later to use some C implementations of that. And there we implemented, it's just plain Python, where we define the serializations just using the plain OpenDAP.
Another question? I'm interested, I'm impressed by the mix of technology that you are using, so there's a lot, and this leads me, so the role, the usability of such tools in the interactions with users. So how are you, what are your views on how to teach your users to train to use all these ecosystems? So did you detect it? Did you discuss with them any survey, any way of doing? Because from my experience, when you put all these things at the beginning, if it's quite radical using Dask, and it's quite different on the previous way of working, so it can be a little bit, the change, the adaptation to change can be difficult.
Yeah, that's a good question. So many of the things were already running, like we need to go to containers, we need to have services, that was already there. So myself, I'm also from more the data science perspective. In our group, we developed that from our needs. And we are not imposing, not yet, anyone to use it. But the idea is that it should really help us, that we solve all these data handling issues in one place through this import service, and everyone can benefit that with very easy to use API. So it should leverage the work and not provide more. And it's building from the people who is using it as well.
Okay, and regarding, is that open to general, or is right now is still internal, or what is your policy? This is a public service for everybody, or how?
So we are also thinking about doing this Python library, like the kernel where we do this zarr and XRI conversion with our data format. That could be open source. That would.
Or I was mentioning more the API because I checked this URL, the discover MeteoSwiss.
Yeah. No, that's still internal.
It does still.
That's another thing. Also in MeteoSwiss, it's an issue of the open data. So, well, doing all these services, we would be closer to open our data as soon as it's needed. But we are still not there.
Thank you very much.
Thank you. So our last talk this morning is from Donatello Elia from CMCC.
Hello everyone. My name is Donatello Elia. I'm from the Advanced Scientific Computing Division of the CMCC Foundation. And today I'm going to introduce some of the challenges related to high-performance data analytics that we've been working on and the latest developments in the OFIDE framework to address these challenges. So briefly, this is just the outline of the presentation. And I would like to point out that this work includes the activities performed by multiple people working on different projects, CMCC, and this is just a list of people that thank for their contribution. So as already mentioned during this workshop several times, decrease in the data volumes and complexity has been causing a radical transformation in the scientific discovery process in several domains, of course, also in the climate science domain. So
could you?
Okay. Yeah, sorry. So from this point of view, high-performance data analytics solution can effectively support climate analysis at scale, since this allows to run basically data analytics on top of HPC infrastructure. However, and this can be effectively enabled through the convergence of high-performance computing and big data analytics. However, the big data and HPC software ecosystem have been developed mostly independently, so this led to a certain divergence in the resulting software ecosystems. And so several challenges must be addressed to effectively support HPDA at scale. In this slide, try to summarize some of the key points that we've been working on. Of course, this is far from being exhaustive. It's just a list of key assets that we've been more interested in exploring upon which we've been implementing some extension to the OFIDE framework in order to better support HPDA for e-science. So all these challenges refer to basically the same common denominator, which is the increase in the scale of the data, the complexity of the infrastructure, as well as the scale of the analysis on its own. So one of the key points, which is the first one, is that in order to actually support HPDA, we need high-level interfaces that try to hide the infrastructure and the underlying data complexity, and thus leaving the user only, let's say, so that they can have an interface which they can use to actually work on science rather than all the details concerning the data management and access to the infrastructure. Another important point is, of course, to reduce the data movement by trying to move the analysis closer to the data, because as the scale of the data increases, as we also saw in the previous presentation, the cost of transferring this data, both from the in terms of time required to transfer data, as well as the power consumption to transfer this data, is actually increasing. So several solutions can be applied to address this challenge by, for example, moving from a client-side based approach to a server-side where the computing components are close to where the data is stored and published. Another important aspect to address is that as the scale of the data analytics grows, the support for workflows that are able to automatically parallelize the execution is becoming very important. And then, as a final step that added to this slide is that in order to be able to run this HPDS software stack on different infrastructure, and not only high-performance computing but also cloud, an important point is to be able to support an easy portability and the deployment of the software stack. So very quickly, I'll introduce the OFIDIA framework, which is a CMCC Foundation project which addresses challenges for easy science with a particular focus on climate science, although the platform has been effectively used also for seismology and biology data analysis. And it provides a high-performance data analytics framework, joining high-performance computing paradigms with big data analytics approaches. It provides this server-side analysis, trying to move the computation closer to the data center and supporting memory analytics. It defines an internal multidimensional array-based storage model, which allows to partition and distribute the data on multiple nodes, and it leverages the data cube abstraction to make the processing of this data easier from the end user point of view. And then it supports multiple type of analysis, ranging from interactive to asset workflows. So in the last few years, we've been trying to evolve the original OFIDIA architecture in order to better support large-scale HPDA use cases. And this slide shows the refined version of the architecture, which is being designed to be modular, so that it can be horizontally scaled with different components based on the actual workload. And it provides as main client-side component a Python interface, which provides a high-level API to interact with the rest of the infrastructure, which is the server-side part of the framework. And we've defined a runtime for executing parallel data operators, which I'll show in the next slide. And as mentioned, it support in-memory data analytics, providing the data cube abstraction, and the data is basically partitioned and distributed across the I/O and analytics servers, which are on the third layer of the architecture, and these are managed by using a key value approach. So we define this new runtime for the execution of the operators, which provides this is an execution model which is built with two levels of parallelism. So the first one is the data cube level, which allows to execute multiple operators on different input data. And then for each single data cube, there's this second level of parallelism, which is the fragment level, which allows to work in parallel on the different fragments composing the data cube. And so we exploit multi-thread and MPI in order to scale into the single node and even outside as a single node by using MPI. We've run some benchmarks in order to understand the levels of scalability that we reach with this new runtime, and this has been done by using praise allocation in the context of the Center of Excellence, in particular the EasyWays Center of Excellence, and has been run on the Milan Supercomputing here at the BSc. We run multiple strong and weak scalability tests by using some of the most representative operators. And we noticed that until 3,000 cores, about 4 terabytes of data, scalability remains quite good. And then after that point, there's a slow decrease in the performance. And we're now evaluating why this change happens, and we plan also in future to run as soon as we address this issue, to run larger scale benchmarks and also try to compare the OFIDA platform with other similar solutions. Beside the execution of simple operators, the framework supports also the execution of data analytic workflows, and in particular, it supports the execution of direct acyclic graphs, which are automatically handled by the workflow manager. And so it basically executes the task based on their dependencies, and then the runtime, which I showed in the previous slide, will take care of running concurrently these operators. We've defined JSON representation to build these workflows, which support different abstractions such as iterative execution, parallel execution, and flow and error control. And the slide shows some real workflows that have been implemented with the OFIDA framework. Another important point that we've been working on is the effective integration with the HPC infrastructure. And so we wanted to provide a flexible mechanism in order to start the computing components of the framework on the cluster nodes, so that user could decide on demand the amount of resources that were needed for the analysis based on the actual workload. So through this very simple interface, the user can define, for example, how many nodes must be dedicated for the analysis, and this allows for horizontal scalability of the framework components. The framework will take care of interacting with the HPC best scaler in order to request the allocation of the nodes. As an additional step, looking also to support an easier deployment of the system, we're also evaluating the use of containers as a layer to enhance the HPDA application portability. And with this, we mean not only the framework on its own, but also additional modules that can address, for example, data visualization and post-processing. We've been carrying out this activity in the context of the EGIS project, where we are building this proof of concept and trying to integrate the framework with high-level software such as Jupyter and other Python libraries. And this will provide the users with ready-to-use configurations of the software stack, leading to the definition of a novel cloud-based service model, such as high-performance data analytics as a service. And it's important to mention that we not only target to run this on HPC resources, but also on cloud resources, so exploring different containerization technologies according to the infrastructure. As mentioned in the challenges slide, high-level interfaces are very important in order to simplify the end-user work. So we defined also for the framework a Python module which is called PyOFIDIA, which allows to interact with the computing components. And the goal was to provide them high-level API, but still have enough flexibility to handle all the features provided by the framework, including the deployment of the infrastructure, the distribution, and the parallelism of the operators. And API provides also virtual objects, which basically refer to remote data queues handled by the server side, and can be easily integrated with Jupyter notebooks and also with other Python modules. Here's just a simple example showing some of the key features that have been introduced in the previous slides. So thanks to these APIs, we can, for example, define the size of the cluster I want to use for the analysis. And then we can specify, for example, with the number of hosts and number of fragments, the data distribution and that we want to exploit for the analysis, and then specify also the number of cores and threads that can be used by the runtime for the parallel execution. And the data can also be then transferred from the server side to the notebook, for example. And from this point of view, we're also working on some extension in order to provide the conversion from the OFIDE format, for example, to other well-known formats such as XArray or pandas. OFIDE is also part of included in the EasyWays 2 project, which is one of the application considered in the data work packages. In particular, this it supports the HPDA use cases in the concept of post-processing analytic and visualization application, and it's been extended to integrate the Earth System Data Middleware, which was also mentioned in the previous presentation, in order to support, in particular, parallel I/O over heterogeneous storage systems. And starting from this integration, we're also developing some extension for in-flight analytics, which aim to run the analysis while data is being loaded from the storage system. So basically, we have extended the OFIDE I/O and analytics servers by connecting these to the ESDM API, and so by building new operators that can load and store data from the ESDM storage system. With respect to what we traditionally use, which is the NetCF format, and this will allow transparent access to different storage backends by using the same API. And then from this integration, we've been using the streaming interface and develops a set of in-flight analytics kernels supporting subsetting and other data reduction functions, and this with the aim to reduce the data that is being moved from the storage to the compute nodes. In case this feature can be also even more effective in the case of the storage backends supports an active storage solution, and hence the analysis can be actually offloaded to the storage system. So before concluding, I also want to discuss another activity in which OFIDE is involved, in particular in building end-to-end Earth system model workflows, and this is done in the context of the Pillar 2 of the eFlows for HPC project, which aims at delivering a software stack integrating different components from computing, data analytics, and machine learning, providing overall workflow management system. So at CMCC, we are working on the integration of a global climate model, the CMCC CM3 model, together with some post-processing analysis for feature extraction and for example, for extreme events analysis. So we are using OFIDE in this case for the computation of extreme climate indicators. And the goal is to integrate OFIDE together with the model simulation. So as soon as the data is being produced by the model, the framework can be used to start computing the indicators. The workflow includes also a machine learning part, which includes a neural network for extreme event analysis, in particular tropical cyclone detection. To conclude, we've been doing some extension to the OFIDE framework in order to better support HPD application, and the first results of the extension are promising, providing good scalability and also integration with in-flight analytics, although still in a preliminary stage, showed some to be effective. And continuing on this activity, we would like in the future to start testing in-flight analytics on large data set, and also potentially also using active storage solution to dispatch the processing on the storage servers, and see if how the impact of this integration. And then we would also like to try to extend the framework with additional storage and I/O solutions such as zarr and FFTB, as well as exploiting novel technologies such as non-volatile memory. And then to try to further reduce also data movement, we'll try to explore also the usage of the framework with in-situ and in-transit approaches, so that we can access the data as it's being produced by the simulation. And this concludes my presentation. Thank you.
We got one question from Gabriela, who's in the room. Yeah.
Yes, I was wondering if you have compared this solution with, for example, a Dask, which is also thought to be easily parallelized.
No, but that is part of the future plans. As soon as we fix some of the scalability limitation that we saw in our benchmark, we try to compare the results of the framework with similar tools such as Dask, for example, and see if, how they differ in terms of scalability and execution time.
Thank you. Any other question in the room? So I have a question. Can you say a bit more maybe of what you're seeing on the pros and cons of installing the framework on the HPC directly compared to, let's say, a server that would be attached to the file system or an analysis platform, and what could be the challenges of installing on the HPC for someone who would like to install the framework on the HPC?
Okay, that's a good question. We've been actually working in order to make execution on, for example, cloud-based servers or high-performance computing nodes transparent from the point of view of the users. And we have been exploring the use of containers in order to support portability, so that the deployment of the framework could be done in the same manner from the user perspective, at least on HPC and on the cloud-based solution. It would be, let's say, the API for using the system would be the same, but internally the framework will interact with different resource managers in order to deploy the components on the node. So, for example, in case of cloud service, we have doing some work like using Kubernetes in order to deploy the containers on the cloud servers, whereas on HPC we've been working with like Slarm and LSF as a sort of a resource manager to deploy the components on the cluster nodes. So it should be, let's say, transparent from the point of view of the user.
Okay, thank you. Is there any other question in the room? No? Thank you again. And now we got a bit of time for discussion on that session, yeah?
Yeah. Unfortunately, we lost the two remote speakers, so the discussion will take place online. And so we have some time. I don't know if we will cover. We have in the schedule 1 hour. I don't know if we will cover, but at least we try. There will be also some time to close the workshop. So, do you want to begin? So to begin, we had at the beginning of the session 2 talks regarding the data compression approaches from Milan and Xavier. And in fact, I was wondering, because right now those 2 activities are quite a research activity, I was wondering which are the approaches to bring from research to production. So what do you think is still needed regarding, but not only technical, regarding also, I think, perhaps on training or on formation on, I don't know, so if you can.
Yeah, I find that a very difficult point. Maybe because I'm very much on the research side, meaning I'm usually quite naive. I like breaking changes, and I know many other people don't do that. I get it. And so I think often it's really a lot about communication, right? So like I can imagine a lot of different ways of how we can do this, but if I don't get kind of like the boundary conditions of like, it has to be that fast, it has to be like that small, it has to be, and so on and so forth. There's basically a massive space of possibilities what we could do, but once we actually know from the operational side what the constraints are, it's much easier to kind of work towards that and find the best, like from the research side, find the best in that. So I think, yeah, depending on what application you actually use in the end, it would be, for the research side, really good to know, like, these are kind of the rules of the game, and try to be as best as possible within these rules. And in the last years, I've definitely, I mean, obviously some of the things you figure out, like this are kind of like the constraints, but in general, if that would be like nicely formulated and kind of like, yeah, by the way, but you should also be aware of this, that would be really great, at least from my perspective.
Maybe I can, you want to say something, Luis? Yeah?
I think if time progresses, people will automatically get more pressure on doing compression because size of data will not get smaller but bigger and more, and price of disks or spinning disks will not scale with that requirement. So it doesn't matter if people like to or not, they have to do it in a not too far future. I see one problem, and that is if you look into the NetCDF developing mailing lists and things around, that they have serious problem with HDF5 group, or the HDF group. And they're even envisaging dropping HDF5 in the sense that they support it further for writing. And that might have a serious impact on using filters, because NetCDF itself does not support this, and it's a full HDF feature. Instead of using HDF, they propose zarr, which might be a better choice. So you should definitely think on a long-term strategy in this vicinity, and it's not that easy. And I would claim that the CF convention people are not the fastest in the world on reacting on substantial changes. So getting new variables is not a problem, but anything else is pretty slow. So I think it will take quite some time to get them convinced to do something. But you can solve your problems pretty easily by just using grep, because it's almost the same what they propose. Only people think it's less usable. But if you use tools, it's fine. Have you ever tried to do an cut of a NetCDF file? Because people say grep is unreadable. So even to use grep, you need a library. And with a library, you can use NetCDF. With the library, you can use read grep as well. So there's no fundamental problem with this. So it's mostly that people are a little bit afraid of doing things slightly different than before. And I think that needs quite some thinking to get better organized in this direction.
I think there is also another important factor, which is a psychological factor, because so far in the climate community, people has used lossless compression, so start losing accuracy in your data. It's something which I think it has to be accepted. I mean, there is an important exercise of the community to understand that your data will not be as it is in the raw output, but losing accuracy is, well, something that it will be necessary and mandatory, I guess. So yeah, I mean, this is, I think, is a change of philosophy that it will be somehow, hard to accept, but it will be necessary.
Thank you.
Yeah, just a comment on grep. At the end of the day, it doesn't matter as soon as everything is working fast for the data analysis, right? For data storage, grep may be perfect, but for data analysis, it's as slow as hell. I mean, and
No,
the tools are not mature.
that's not
I mean,
true.
You can do it fast, but that you have to prepare the index and blah blah blah, right? So that's an extra step. And if the libraries and the tools will become mature enough, I mean, why not? It doesn't matter. As soon as data analysis, people who do data analysis can get the multidimensional array quickly. Access to multidimensional array is fine. That's one comment. And about the accuracy, like for your when you're doing the model, in principle, grid scale information doesn't really provide you good information. So we just it's also should be a change in the people's mind that you don't really need one-to-one lossless, useless information on the grid scale. And also, if we're targeting the application community, as we do, for example, in this in many of the initiatives, including Destination Earth, is that for applications that will calculate the impacts of, I don't know, floods or well, maybe extreme is a different thing, but like, I mean, increase in the temperature. If the temperature increased by 1.235 or 234 degrees, I don't think that it makes any difference. So, and that's what you can easily achieve with a lot of compression.
I don't know, Luis, you want to react because you were so.
Yeah, quite some things. So I'm from experience, I know that grep is not slow. It depends on if you have a proper workflow or not. That's one of the central things. You don't need an index in general. The other thing is, I fully agree, or let's say in that way, the climate community is not that separated, and grep is compressed all the time, lossy, and people have not really complaining against it. It's more that you think you are precise, but climate science is not precise in the floating point precision thinking. So you can circumvent that, but as you heard before, there was a question on benchmarking the compression with different workflows, analysis workflows. So just pass them on, the information on what workflows you would like to see and at what precision, and you will get the answer if you get 6 times, 7 times, 5 times, 4 times, 10 times, 100 times compression rate. And when you think back on the discussion yesterday on power consumption of things, you should definitely think on what you store, because prices for disks are high. As more disks you need, as more power you need. And the key issue is not talking about energy consumption. The key issue is reacting on this and changing your workflow in a way that it saves energy. So forget about passing on information in megaflops per second or whatever. Please go over to picojoule per flop, or picojoule per byte, or picojoule per byte per second. I think that's something we can easily do, and then we can think about how to do things. So the question is consequences and not talking about the things.
Yeah, I just want to add that grep can also be fast. It's just how we structure them HPC. For instance, if you chunk them and store them as small blocks, you can still get the same speed. And then the problem is tooling. Can tool handle it? That's the thing. And I think that's a problem with grep. Generally, the tooling is, even to install grep, not always it's easy and whatnot.
Yeah, just it's exactly the thing. And I'm saying that, like, you can make everything fast, right? But try to open it at X-ray. It's slow. That's what 95% of the people going to try to do. And that means that the second they try, like the 5 minutes after they try to open grep, they will just say, okay, thank you very much, bye. I need my netcdf file.
But on the other side, I find zarr more clean specification, that it's not cryptic. Like grep, you have to write message and you have a variable name that you have to find what its name is, what's the code for it, or all kinds of things. Zarr is more clean. It's just a metadata with a just binary dump of things, and you can compress it or don't compress it. It's your choice. It's much more cleaner than grep. Grep can be a filter of zarr because it's just a byte stream of things. I don't know. It feels much more clean than just using grep. That's one. And even before we go to the lossless compression, I think we haven't, lossy compression, we haven't even realized the potential of lossless compression. because most often the lossless compression that we use is netcdf and compressing the whole file, big file. Instead, if you compress chunks of it, you get much more compression ratio, and we haven't been using it at all so much. Even before we go to the lossy, we didn't even try so much about lossless, even, is what I thought.
I wanted to come back a bit to the quantization aspect and how we go to the lossy compression, and you were asking what do we need in the community from the research side. I think when you assemble an ESM, there's many layers of expertise. So you've got people who will be developing some microphysics, some people who will be developing the atmosphere, some people will be assembling the whole model, and it's not necessarily easy when you arrive at the last level. People who are looking at the operations, how much data you store in the archive, to make the choices and to communicate with the developer of the science. So things that are useful, I think, would be tools that can tell from a kind of a high level, the choices you have made may not be very good when you decide your base or your range for your lossy compression. So I don't know if you had some thought a bit on that or.
Another comment, NCAR is doing research on compression of data since 2013. They published several articles. You can look for the articles from Alison Baker, for example, in 2014, 2019, and in between. So there's quite some research, and that's lossless compression, where you can check out what they did. For example, SZ was part of it, FZIP was part of it, and a lot more. So it's just reading literature like normal in science. You should get a better overview.
Sorry, any further reaction? So, I don't know if you want to read what Brian, because Brian contributed, and I think you will read, if you want to read because he explained.
Right. So Brian said, I cannot be in the discussion now, unfortunately. But I think a big issue with the zarr netcdf PanGeo workflow is that there are really good reasons why we like both netcdf and zarr. And so tools like Kerchunk are really interesting. We would also argue that CF aggregation, which allows a netcdf file to point to other netcdf files in conjunction with ideas from Kerchunk, will offer a unifying way forward. We will talk about this next time. So we should go. I don't know what Kerchunk is, so I don't know if any.
Yeah, maybe just also one comment about coming back to tooling and how this thing can be implemented. Like a lot of people here, I think from the really workflow perspective that we have an experiment, we run it for 30 years, we put it somewhere, and people do analysis on it. And in real life, that kind of CMIP6 workflow, but like PhD students and postdocs and projects, they just run the models and don't have, like, the only workflow that they have, just start the model and start to look at the output. So if these things probably have to be included in the model code, so it's not something that in the post-processing, because as soon as this is possible for a person who runs the model to have at least headaches as possible, it will be turned off. But if it's just a flag in the name list of the model, it's a different story. As soon as we just include it there, then it's gonna be used. If it's some external thing that you have to convert your produced data to then lower amount of data, it's gonna be used much less, and only for maybe these big long simulations that are really production runs, but not on the main of the data that we generate.
Yeah, in fact, I totally agree. I think it's many of us, I think we have this idea of these convergent workflows that are gathering everything, and we are. But I totally agree. But then, then there's the risk, and it comes from the comment that I was telling that in the talk from Gabriela, that there's also, when we produce the data, there's also the view from the users, how we can bring them to really use all this. For example, something like easy like a workflow. If they need to configure, they need to know that there is this flag, and they need to know that there is these tools, and there is the will to change and to use this new technology. So my question is to know if you have, which is your view and how you are doing in your institutions or at home to bring the users to use these new technologies. So if you have ideas or if you want to share your experience.
Maybe to be an annoying guy here, it's really hard also to make people to use like simple compressor. I mean, you have an NCDF, you just can do this minus z and say okay, minus z2, and it will be for some fields it will be 2 times smaller. But the thing is that in the post-processing, and people want to look at explore the data, it will be slow because you will have to unpack it all the time. And as, again, users, as soon as it's possible, will just turn it off. Because then they will be, it's exploratory data analysis. It's like you have to be as quick as possible from the idea to the figure. And if there is something standing on your way, and forget it. The science will not progress.
Yeah, so maybe to your answer, so the way we are proceeding now, it's also not trying to impose anyway. So we are trying also to put on the table all these issues we face when trying to do that analysis. So I think the first point is starting to talk about it. Then, because, well, from our perspective, many of these operational issues are still not very dealt with or discussed with in the community, like MLOps concepts and so on, strategies which to follow in this weather and climate community. And so first putting this problem into the table, and then I think like progressively we still also want to know if it's good enough for our problems. If it is, then we can also, of course, give visibility so that maybe try it for other users close to us and progressively see if it survives of these use cases.
Thank you, Gabriela. Any other comment? Yeah.
Maybe a general comment on this whole idea of lossy compression. Because, I mean, at the moment, basically, if you download data from ECMWF, you can either get it as grip or as netcdf. And yes, both of them somehow contain some kind of lossy compression. And the question then is obviously, even if you follow this idea of like information preserving compression that I presented earlier, at what point is the precision that you throw away going to be so hurtful that people actually complain and say like, hey, I can't do my analysis anymore. The results are not useful anymore. And so the question is then, do you, in this meantime, where you try to explore exactly what people need, do you basically provide 2 data sets and say like, this is the high precision, this is the low precision. The low precision is smaller, you can download that one. If you feel like you want the high precision, okay. But then in this meantime, in this intermediate time, you basically have an additional burden on your data archive, right? Because everything has to be stored somehow like twice, or has to be like truncated while people want to download it. And so I'm actually wondering, because this is somehow already happening anyway, why wouldn't be a strategy where you say, we started at the, let's say, like this given precision that we have right now, and then let's say, I don't know, every couple of months or so, you basically go down in the precision. And so basically over this time frame, people have time and resources to kind of like check. And if they somehow feel, oh, there's something happening, which we can't work anymore, where you actually cut away precision, then you basically have like enough time to react to kind of stop that truncation of the precision over time. And so hopefully you then end up basically with something where you not like directly jump to very low precision and people start complaining, and therefore you basically produce some kind of model results in the meantime that are useless, but you basically gradually go down, and by doing so you gradually save space and have time to basically have people to analyze the results and see whether there's any problems with that.
So unfortunately, it works often in the other way around. So when we're organizing the production, we enforce a level of compression, and people start to complain, and that starts to creep up uncompression, where scientists ask more and more. That's not good enough for me. So unfortunately, it's often the reverse process that happens in practice. Yeah.
But what they complain about? Why they are not getting the compressed data?
Well, something that happens is we like, for instance, in things like chemistry, there's a lot of different ranges of variables, and one of them will not fit in the range of the compression we've defined, and they will decide there will be a blanket uncompress on the whole stack of variables to make sure that doesn't happen. Yeah, these kind of things.
More accuracy of the results.
Yeah.
Not like speed of the working with.
No, it's more accuracy of the results. Yeah.
I think some of the things Milan said is cool in the sense that because it's exploratory, your compression, for example, you don't know, in some cases it may not work. So meanwhile, there could be an approach, for instance, the same example, ECMWF gives files to download, and there's an option to download reduced precision output, and it's done on the server side on the fly, and then you get that version and you use it, and then when you go through exploratory analysis and you have some hypothesis, and then you get the bigger version, you tell the users, you can get the higher version, you can cross-check, and please let us know. And then that's where you can take the feedback and see how many people use what kind of versions and how do they download and how do you evolve forward. But asking ECMWF to do that is...
Yeah, I think there's actually a big incentive on the user side, right? If I have two files that are supposedly the same, and one is 1 gigabyte, the other one is 10, I would be like, oh yeah, let's start with the 1 gigabyte file. Great, I can download that, see what's happening. It's kind of like the same structure of the data. I can have a look at it as like a preview. And if I'm absolutely happy with that data, then I'll just go for it and I forget about the 10 gigabyte file. But if I feel like, oh, maybe there's something odd, then obviously people may make this. But like simply because one file is so much smaller than the other, there's an incentive to use that, right?
I don't know. I was thinking when you were saying that, I can imagine also cases where if you put these two files, some users will go directly to the high precision by default because they will have this a priori that perhaps in the truncation they lost something, that it's a risk. So they will. I think it's quite. We can do the parallelism also with the precision on variables, so that we went to using high precision, this double, instead of going down, and there's a fear that we broke something, and if I broke something, I prefer to underperform, but I'm sure that I'm doing the same thing as in the last years, and I know that this works. So
I think mostly for remote analysis, maybe this is one, like data is at ECMWF and I want to analyze here. I think start from there. I think they don't have to do anything. They just have to, and then you can track the metrics of how many people use what data version. Do they use low or high? I mean, it's a bit dreamy, I think, but still, it may give some insights into, or somebody says, oh, I don't like this variable compressed in this format, and I think it's an incentive for users to, it's faster analysis and whatnot.
I think the only good way is actually to show that it actually works by different examples and showing by doing. So just relying on users experimenting, it will take years for them to actually change this line in the script that downloads the data that they inherited from the 5 generations of PhD students before. So it's only, I think in the beginning you have to show several use cases that it's actually working for very nice. And putting it in in the things like I think it's Google Data Store or Amazon. I don't know who hosting this CMIP6 bunch of CMCC data. It also can be a good way forward. Or some, I don't know, some European cloud. But relying on the users experimenting, it's really not a good way.
The thing there is that you store
Conservative.
multiple copies then, and you don't want to do that either. So somehow, but
Any other topic that you would like to bring to discussion? Yeah, go ahead, Luis. Say something.
Again, going back to the power consumption discussion from yesterday in this area, you can easily solve the problem by storing the high-resolution data on tape archives. That's cheap. No energy consumption beside production of the stuff, and maybe a little bit during recovering. And if somebody would like to have the high resolution, you have to drink a lot of tea, and then you get your data. But that's okay. I mean, at the end, it's a price tag you have to look onto, and most people are reacting on price tags. If they have to pay it privately, if they don't, well, then the price tag is given by the computing center, and if they say they cannot store the data, we can do it in a slow way, then you have to live with it. Then it does cost time. Who cares at the end?
I will just react on this. I mean, tape is not free, so it has a cost too. So it's we do have to manage our tape archive. We cannot store everything on tapes. We do have to delete data regularly. Yeah.
Do you have a statistic how many data I actually retrieve from the tape archive? Because I remember from DKRZ, there was some numbers that basically tape archive is a dumpster that nobody, like the data that comes, nobody use actually data from the tape archive. Almost nobody. Because I mean, a lot of science will not be done. Because the cool thing about having your high resolution data on the fast disk is that you can go there and in one day have the analysis of something interesting. If you know that you will get something from the high resolution data, that it's not exploratory science anymore, it's just operational thing. So, I mean, I'm all for like more efficient data storage and so on, but from the exploratory science point of view, having data on the tape archive means that they will be used much less, I would say.
So I wanted to formulate a question here for those that will be involved in CMIP7. So what would happen if a model, let's say EC Earth, decides to store the data, it's summarized and everything with 16 bits, all variables except, say, precipitation and 2 or 3 more, or even less than 60 bits, if we can, would it mean that that model is not going to be used in any intercomparison? So I'm going a bit along the lines of what Luis is saying. So this is what you have. Probably I wouldn't even go down the route of the tapes. Don't care. So this is what my model has. If my model is good, it will be good at 16 bits or at 64.
Certainly will be used. I mean, that's no question about that.
I mean, maybe there'll be something for, I don't know, to think as a community, a data request, or how you define the precision of your data, yeah. But that requires some community effort, yeah, I think.
that's actually also another place where you can actually reward users, because there are a lot of CMIP downloads. And then you can say, user, you can use this version and you'll get all the data and you can use it fast and everything's great. And then I suppose people will use that and they won't use the higher precision because it takes a long time to analyze, because a lot of people download too. And then all those users will.
Yeah, so I was trying to be provocative here. So I'm not saying that we shouldn't consider some use cases that are special, like, variables that are spiky and things like this. So that's obvious. But I wouldn't go down the route of asking the users, what compression are you happy with? But this is the compression. If you're not happy, you have to make a very strong case for it. I think it's ridiculous that our community has been storing geopotential height at 200 topascals with 64 bits. To be honest, I think that's an insult to any intellectual person. So I think it's enough, and it's a matter of responsibility.
Yeah, so, and coming back, I think I want to react to the discussion regarding tapes. I think we have the experience here at BSc that once you put the users that they have to manage themselves tapes, it becomes, I think, a little disaster. So because they don't react, we tried. Personally, there was at the beginning when we implemented an automatic system that everything that was put it on in a folder would be on tapes, and I decided that this would be really against our users and this could have a lot of impact, and I decided no, we created like a layer where they could do petitions to send and to retrieve. And after 1.5 years, I realized that even if we created this script very simple with only 2 parameters you move, we are still having issues with our storage. And I'm sorry, but we'll need to move to the automatic way. And if finally the users are impacted, it's the way it is. They will learn on how to work it. But only to bring this idea of if we ask to users, if it's very nice, but if we ask and we want them to participate, not always this is working. And sometimes we need to be much more proactive. And in the way that Paco was doing, that this is what you have, you need to use it, you need to learn to use it. And then perhaps we don't make friends, but it's not.
Say a particular storage is automatically tape archived after a week or so, and build better tools for retrieving data from tape. I think all the tools I used in the past were not of that great. I think we could also invest time in building nicer tools to use tape archive.
So far, the best tool I saw is on Jules. It just looks for you as a folder.
Yeah,
that's the best thing.
Yeah, because it's transparent at the end. Yeah, but then when in this special case, for example, is it transparent, but the user will understand that it will take, they are used to do an LS and to retrieve and take milliseconds. In this case, if it's on tapes, they will not probably understand at the beginning that it will take a few minutes or some time to retrieve. So personally, I was worried on this, but now I change it, and because I'm losing my time and I'm losing my effort because the user, I'm not blaming someone in particular, but because they don't want to put, so I think time is important. Luis?
That would be a perfect case for machine learning. You could set it up and you could give the people an estimate how long it will take till they get the data they ask for.
Yeah.
Because when they know, okay, I have 2 hours, they can go either for lunch or drink a coffee or 10 coffees or 100 coffees. And maybe the request is gotten over. And if you got the answer back, it takes 2 months, then you know, okay, I forget about it because in 2 months I have forgotten my question.
That's actually will solve actually a lot of problems. When you know how much time, it's also that's similar for if you submit the job, you see, okay, in 2 hours it will be probably working. It's much more satisfying feeling when you can plan. Otherwise, you don't know, should you wait for it or should you, I don't know, go and read publication?
Yep, and maybe it's a super simple and very easy machine learning exercise.
But you also prefetching, I think in the prefetching the data also does. Right?
Yeah, you have a cache on disk and it will prefetch and the data that is still. But I think it's really nice that you bring this at the end. Is the feedback that we do we give to the users in tapes. Usually, it's embedded to a terminal, so it's not the user does not get many information. Still, for them, is really this understanding, these different layers of storage, it's something they will say that for them they already have many other things to solve with their science and their projects. So if you put this, they will not understand, and they will do an LS and the file is not there, and then they will go to Slack and send something. So
but what if when you say, okay, I want to copy this to storage, as an option you just say, okay, I also want to compress it. And if it's just an option in this copy routine specific for their system science, that I think will be also used much more, because nobody is against it at the end of the day. It's just the time and effort that you have to spend.
Beware with options, because users tend to disable the options. So this is something that we discovered with options in workflows. We had very nice options that send at the beginning all the data to storage and then retrieve if you need it. And we realized that nobody was using, because we don't even publicize, and we said we put this parameter, and they managed to discover it, and nobody was using. So, any other topic that you would bring, or I think we can conclude. Yeah, I would like to appreciate. I think it's not always easy after 2 days and a half discussing about HPC, this session on data and having this discussion, but I think it went quite well. So thank you very much. So now, before leaving, if Sylvie, you want to come, I think we will do the close. I will do as usual. As each day, I will do a little bit of housekeeping, some very minor details, and then we will do the closing and some words. So first is regarding slides and recording. So please, the speakers, upload your slides if you want to change before tomorrow, because Sophie Moguellon will update the website, in the ENES website, and there you will have the abstracts and the slides. If you don't want to have your slides or talk published, we know that there is one case, it's perfectly fine. So contact with Sophie, and this also applies because the streaming company will provide the recordings. So before uploading, we will cut those presentations that are not public. Sorry, can I have some? Then last activity, the Mare Nostrum visit. At the beginning, we thought that we had 3 groups to visit, but at the end, that's true that some of you already have been here. There's only 1 group. My proposal at the beginning was to leave at 1:30. I don't know, this makes more or less half an hour to have lunch. So those interested, that I think there are 14. If you want, we can leave at 2 and have a more relaxed visit until 3. So I will be here around if it's okay for you. I don't know if someone from visit needs to leave earlier. If we can move it to 2, is it okay, or you wanted the visit? So okay, so let's move it to 2, and we will start from the stairs, because that's also nice. I will explain a little bit about all this chapel and the building. And yeah, and finally, this is part from the organization. I would like to thank all the people involved in the workshop, starting from the speakers. Thank you very much for your contributions, and your talks have been very interesting. Also attendance, not only on site. I think it has been really nice to meet each other after 2 years, but also all the ones that were remote. The organizing committee for preparing the agenda, for looking for the speakers, and so on. And then the organization itself, I would like to thank you, Mario, Gabriela, Albert, and Sophie Moguellon. Also, session chairs, I think you did a very great job on keeping times. So, and it's really important when doing stream, because we have half of the workshop there with the agenda. And finally, I would like to thank you, and it's really, I think it's really, really important, our web FineStream colleagues, Enrique, Victor, Damian, and Miguel, for the fantastic work that you have been doing during these 2 days and a half. You did a wonderful job. I think everybody could follow with remotes, the discussion. I was really impressed, so thank you very much, and it has been a pleasure.
So just a few words. So thanks also all for your participation. Sorry. And we started those ENES workshops in 2011. We have practically been able to run them every 2 years, more or less, using EasyNES first, and then when EasyWays came, we had the interplay between EasyNES and EasyWays. I think this workshop shows that it is really useful to have this kind of workshop dedicated to HPC for the Earth system modeling community. I hope we can continue them. It is planned in ECMWF 3, I guess. And because I feel that the fact that now more and more the activity is spread in many projects, so the fact to have those meetings where we gather the information, share the information from different projects, I think it's very useful to have those. So I hope you enjoyed it. Sorry, I hope we will meet again. And sorry, I have no more voice. Before stopping, I would like to thank Kim, because really Kim is the key organizer, the one that is behind all this. Yeah, not alone, but you really kept it ongoing. So thank you. Have a good trip back.
Thank you. And now lunch, I think, will be served. I think it's already there, so 1-1. Thank you. And only last practical details, though.